Good morning, everyone. Good morning, and welcome to the third edition of the annual SDSC-Connect event. My name is Olivier Verscheur, and I'm the founder and executive director of the Swiss Data Science Center, or SDSC. I just want to start maybe to get it out of the way, if you will, with a few words about the SDSC. So the Swiss Data Science Center was founded in January 2017, almost 4 years ago now, and it is a joint venture between two world-renowned engineering schools in Switzerland, EPFL in Lausanne and ETH Zurich. Our mission, as stated from the very beginning, is to accelerate the adoption of data science, machine learning methods, and AI in academia and industry. And to address the challenge, we've been hiring, and are still hiring, a dedicated team of talented scientists. We're close to 70 collaborators now, not counting students, to bridge the various gaps in the data science journey, working hand in hand with both labs and industrial partners across Switzerland. And this is enabling adoption of data science at a scale only possible when pooling resources together. But enough about the SDSC, and back to today's events, enhancing discovery and creativity with AI. A very hot topic, illustrated, by the way, by the number of registered participants to today's events. You are over 400. There's a lot of buzz around this particular topic. Sometimes maybe too much buzz, that it becomes very difficult to truly understand what is today, or in a relatively near future, actually possible to do with AI and what is not. But maybe to best talk about it, given that she actually led and put the program together, I'd like to introduce you to Dr. Silvia Quarteroni, a principal data scientist at the Swiss Data Science Center. Silvia, the floor is yours.
Thank you, Olivier. Welcome, everybody. I have the pleasure today of walking you through the agenda. Indeed, the primary motivation that was beyond this event is the fact that we know that many of you already use machine learning in your daily working lives to optimize processes, for example, in the industry, or to have better insights on your patients or customers. But what is perhaps lesser known is the contribution of artificial intelligence to tasks that are typically associated with the realm of creativity. For example, creating a fragrance or designing furniture, but also the contribution of AI to discovering new products, including new drugs and medications, which it would take much longer to come up with more traditional approaches. So the goal for today is really to have a few examples of this as contributed by our invited speakers. And I will just briefly walk you through the agenda for today. Here we are. I hope you can all see my screen right now. So this is today's program, which you can access through the swap card application. You will see that we will start with a very interesting keynote from Professor Krause, but more on that later by Olivier. We will then have 3 talks in the morning. The talks will last 30 minutes, and please save your questions for the Q&A chat, live discussions that you can enter right here through this tab. We will have indeed half an hour dedicated to breakout rooms, so individual rooms where you can join the speakers to submit your questions. We will then have lunch break, 2 more talks, followed by a Q&A session. And finally, I will have the pleasure of moderating a panel with very distinguished attendees to discuss the societal impact of AI-assisted discovery and creativity. And finally, we will have our last keynote of the day by Professor Miller. Few closing remarks will ensue. So for today, there is one single track that you can attend using the swap card application, which will be doubly broadcasted as a YouTube live. Just keep in mind that for question time during the regular speeches, you will have dedicated links. So there will be parallel sessions for question and answer, as you see here on my screen, to have the opportunity to have a very fruitful interaction with your speakers. Thank you very much. And now over to you, Olivier.
Thank you, Sylvia. And so speaking of questions, the first keynote, which I will introduce in a second, for the first keynote, please ask your questions through the chat channel. You have a question channel in the live discussions, and please post your questions there. Because of the YouTube broadcast, for scalability reasons, there is a 20-second delay between between real time and what you get, basically. And so to make it easy, please submit your questions, and we have a moderator who will read your questions to Professor Krause. This is only valid for the first keynote. For the rest, they will be Q&A sessions. All right. So with that, it is with great pleasure that I introduce you to our first speaker and keynote of the day, Professor Andreas Krause. And I'm sure most of you know him or know of Professor Krause. But I'll say a few words. After a PhD in computer science from Carnegie Mellon University, CMU, Andreas joined Caltech as an assistant professor of computer science. That was back in 2009. In 2011, he joined ETH Zurich as a professor of computer science, where he leads today the Learning and Adaptive Systems Group. And throughout his still relatively young career, Andreas received an impressive number of awards. I won't list them all here, maybe most notably an NSF, National Science Foundation from the US Carrier Awards, an ERC Starting Investigator and ERC Consolidator grants. He's also a Microsoft Research Faculty Fellow and a KLE Frontiers Fellow of the US National Academy of Science. More recently, his research on machine learning and adaptive systems have received awards at several premier conferences and journals, including last year, the ACM SIG KDD Test of Time Award, that was in 2019, and very recently, a few weeks ago or a couple of months ago, losing track of time these days, the ICML Test of Time Award 2020. Andreas, without further ado, we're very happy to have you start the event today, and the floor is yours. Thank you very much for being with us.
Thank you very much, Olivier. Let me share my screen. Aha, host disabled screen sharing. Can I share my screen?
Yes, I'm sure the host will help you.
Is there something I can do? So it just gives me an error message. Otherwise, I'll have to just vigorously wave my hands. Okay.
Andreas, you should be able to join to
Oh, it looks more promising. Awesome. Okay, very good. Can you see it?
Yes, we can.
Okay, perfect. Okay, so thank you, Olivier, very much for these kind words, for inviting me to speak at this event. It's great to be here, if only virtually. So the theme of this year's SDSC-Connect is how to use data science and AI to enhance creativity and discovery. And that's a topic that's been fascinating me for a long time. And I'd like to tell you a little bit about some work and some exploration we've done around this notion over the years. So just to get started, of course, these are truly exciting times for data science and AI. Machines are getting better at understanding images, speech, language, making progress on challenging applications like self-driving cars, beating the top human players at the games of Go, etc. And of course, one of the main drivers in recent years have been advances in machine learning, deep learning, and so on, right? So in particular, supervised learning, where we're given a data set, say of images labeled as cats and dogs, and we would then go ahead and represent them mathematically, say as points in high dimensional space, fit the hypothesis, a classifier, a linear one, maybe a neural network that we can then use in order to make predictions about items that are similar to those that we've seen in the past. And this is an area where machine learning tends to be very good at. So it tends to work very well if you want to make predictions about things that are similar to those that we've seen before. Okay, now this event is about discovery, and discovery is about trying to find things that are different from those that you've seen before. Okay, so there seems to be quite a substantial mismatch here. And of course, there's the key question now of, given this discrepancy, how can machine learning, say, still help in this discovery process? So I'd like to start with a concrete motivating application. So this is one that goes on back 10 years about now, some work that I started to do still at Caltech. And we had the pleasure and fortunate to collaborate with Frances Arnold, a Nobel Prize winner in chemistry in 2018, who's done pioneering work in an area called directed evolution. So this is a technique of navigating or searching for proteins that have desirable chemical properties, a key challenge in many domains, particular drug design, and many other examples. Of course, one of the key challenges is that there is a large search space of possible compounds that can be synthesized. But the goal in the end is to find specific ones that have desirable properties like high thermostability, high binding affinity, etc. So concretely in this collaboration, we looked at a particular family of enzymes called the P450S chimeras. They play an important role as contrast agents in medical imaging and more general in the drug metabolism. So how does directed evolution work? So you would start with a bunch of parent sequences, enzymes, and then you would go ahead, highly simplified, of course, to break them apart and reassemble the pieces to mix and match in this process, creating chimeras. And then you would synthesize those chimeras in the pursuit of one that works as well as possible. So this is a way of structuring this extremely large search space for possible compounds that can be synthesized. Now, if you consider all these possible compounds that we could create, enzymes we could synthesize, of course, we'd like to find the one that does best, say maximizes a particular functional property like thermostability. The trouble, of course, is there's far too many sequences that we can not go ahead and try to synthesize all of them. So at best, we can try to run a couple of experiments, obtain noisy measurements, and using those, try to find sequences that perform well. But of course, this leads to a key challenge, right? So we are not starting with a massive data set and then make a prediction about a sequence that is basically similar to those that we are starting out with, but we're trying to find good sequences, good enzymes to synthesize. So that means we face this dilemma of setting up experiments to learn as much about this protein fitness landscape as possible while using what we learned in order to guide our search. And this problem actually arises in numerous other domains. So one where this is very common these days and very actively explored in machine learning is a subfield of machine learning called automatic machine learning. So here the idea is to help with the search for machine learning models, neural network architectures, hyperparameter choices for the ones that empirically works best for a given prediction task. And this is necessary because at the moment we still lack the necessary theoretical understanding that would allow us to a priori determine, say, what's the best neural network architecture you might want to use for a given machine learning model. That means in the end, it's very much an empirical exercise where we do have to try and experiment with different architectures to find those that work the best. But in the end, that means we have to conduct experiments, right? We have to try out, say, a given neural network architecture, given hyperparameter settings on a given data set, and test after training how well does it do in a validation set. lots of randomness involved. If we repeat the experiment, we get noisy outcomes. Individual such experiments can be very expensive, right? And they can take hours, if not days, on a compute cluster. And again, now the question is, how can we use machine learning in order to help the search, and to figure out how to make this experimentation more systematic? There's many other applications. So one very natural one where similar exploitation challenges arise is in the context of recommender systems, right? Maybe the most widely used application of machine learning that each of us is facing on a daily basis, right? So if you go online and get a recommendation for a book to read, movie to watch, article to buy, etc., recommender systems learn about our preferences by observing how we and people like us interact with the content that they display to us in order to make predictions about the relevance of items that they haven't shown to us yet. Right? But of course, these systems have no way of knowing whether we actually could have been interested in the movie that they didn't show to us. So the very decisions that they take pertain to the very data that they're being trained on. And again, they have to trade exploration, showing us new content that we might be interested in, versus making use of the models that they learned in order to make better recommendations. So it's really a ubiquitous problem across many different domains. And a common challenge in most of these applications is that the number of alternatives we have to consider is far more than the number of trials that we can ever carry out. So the number of compounds we can synthesize is far bigger than the number of experiments we can carry out and so on, right? And even though recommender systems might interact with a lot of users, the number of interactions they have with any single user who they want to personalize the experience to, of course, is also very limited, right? And they have to systematically discover relevant content for them. Moreover, these experiments are typically noisy and expensive. So this seems to be a very, very challenging kind of setting. So why should there be any hope of applying machine learning? Well, at least a lot of these applications have some notion of regularity or similarity. So we would expect that, say, similar proteins have similar functional properties, right? Or similar users have similar preferences. And of course, the key question is how can we make use that kind of regularity, which of course is at the heart of machine learning. So one way to think about this problem really abstractly is that we have a black box that we can give some input xt out of some set d. So this xt could describe a particular enzyme that we can synthesize. And then we carry out an experiment, which basically uses an evaluation of f at xt perturbed by some noise. And now what we would like to do is carefully plan which of these experiments to carry out, because each of them is noisy and expensive, in order to find solutions of high value as quickly as possible with as few samples as possible. And in general, if you don't have any assumptions about this function f, this is a completely ill-posed problem, right? That should be obvious. So we need some sort of way of expressing or making use of any sort of prior knowledge we might have about this function f. And one very natural way of doing so is to encode prior assumptions, is to take a Bayesian perspective. We might take this unknown function f and view it as a realization of a stochastic process, as one out of infinitely many possible sample paths of a stochastic process of distribution over those functions. That perspective then not only allows to make predictions about similar items, but also assess the uncertainty in our prediction. And this uncertainty can then be used in order to navigate this exploration-exploitation dilemma. So you can figure out where we should sample in order to learn more about f, reduce the uncertainty about f, while at the same time using what we know in order to guide our search towards regions of high value. Right? And so now the key question is sort of how should we think about these kind of sampling strategies in order to discover good solutions as sample efficiently as possible. So that's a classical problem in Bayesian optimization with a number of proposals on how to do that. They all resolve around this idea of using an acquisition function that would inspect the posterior uncertainty about this Bayesian model in order to guide this search. Now, of course, in principle, one can use many such Bayesian models. One choice that's very commonly made in Bayesian optimization are Gaussian process models. So these are distributions over functions that express certain prior assumptions, regularity assumptions about this unknown function, which might say that smooth functions like those here are more likely a priori than functions that disagree with my regularity assumptions. And as Bayesian models, once we have data, we can condition it on it to calculate our posterior distribution. under which functions that agree with both our prior and our data are more likely than functions that disagree with our data or that disagree with our prior. And of course, one can in principle use many models. So Gaussian processes are widely used in this area because they're very expressive on one hand side, naturally allowed to incorporate domain knowledge, yield predictive uncertainty, and have all sorts of nice computational tractability benefits. They also have strong links to neural networks, can be seen as certain infinite width and infinite depth limits of Gaussian process models. Okay, so how can one make use of the uncertainty that these models provide? So here's sort of a key picture that illustrates some of the key ideas. Okay, so suppose we've carried out a bunch of experiments shown by these pluses here, and we've calculated our posterior distribution where the mode or mean is shown in black, and we also get confidence intervals shown in gray here. And suppose we can calibrate them in a way such that the true function shown in the blue dashed line here are contained in these posterior confidence intervals or credible intervals. If we get ourselves in that position, we can apply the following rationale. So let's look at the maximum lower bound, so a pessimistic estimate of the optimal value of that function shown in this green dashed line here. Now we know, since the true function is contained in these confidence intervals, its maximum must be above this green dashed line. So it must live somewhere within these green shaded areas where the upper confidence bound, our optimistic estimate of the function value, exceeds this best lower bound. And that idea is really crucial and can be instrumentalized and turned into algorithms in various different ways. So one way this can be done is to instantiate the celebrated optimism in the face of uncertainty principle. Simply optimistically pick the point that not just maximize the expected function value, but some plausible maximum function, right? So it optimizes the upper confidence bound on our function. And now for Gaussian process models, this yields a super simple greedy algorithm. So all we're going to do is we'll linearly combine our posterior mean, mu t, with our posterior standard deviation, sigma t, traded off using some trade-off term beta t. So this enumerates percentiles, of course, in these credible intervals. And that yields exactly that kind of behavior qualitatively as it's described. So initially, you're mostly unsure about actions. So we prefer points that have large posterior standard deviation that you're very unsure about. So you're seeking new things that are different from those you found before. But then eventually, you make use of the data you've learned and the similarity in the model in order to guide the search towards regions of high value of large posterior. So it very naturally trades off exploration and exploitation and only picks among these plausible maximizers. Now, of course, the key question is how to exactly navigate this exploration exploitation dilemma. If you do it wrongly, bad things can happen, right? So if you have beta too small, you under-explore and you get stuck in poor solutions, right? You don't seek novelty enough. If beta t is too large, then you only seek new things and you don't make use of information that you have in the past. And so it turns out that there is, in fact, a way of calibrating this exploration trade-off that does guarantee convergence of the algorithm. So it does converge, basically provide sublinear cumulative regrets. So the average gap between the iteration t and the optimal value converges to 0 at a rate that depends crucially on two quantities. So one is this quantity gamma t, that is some notion of capacity that describes the effective degrees of freedom of this prior distribution. So if you admit very complicated functions, then you would expect slower convergence. And it also depends on the discrepancy between the Bayesian model that the algorithm uses and nature, right? Because nature might not be drawn exactly from the prior distribution that you use, right? And so those basically show up in the resulting bound. Okay, and so that algorithm actually works pretty well. So let me come back to this protein engineering application. So one nice advantage of this Bayesian optimization machinery is you can naturally apply it to, say, complicated, also discrete index sets like molecules, graphs, and so on. So you can use a covariance function for the Gaussian process model that basically captures prior knowledge, prior assumption that say surface mutations of the protein affect similarity less strongly than core mutations, right? And so one can code this with particular kinds of covariance functions that actually yield pretty good predictive performance. So there's some data that our collaborators collected in wet lab experiments, where at least in the vicinity of enzymes to those that they synthesized, gives very accurate predictive performance and nice Gaussian tails for the noise. Okay, and so now, given this, so they basically run variants of the algorithm. So one additional challenge that I'd like to briefly point out here, of course, is that the basic algorithm I've described is very sequential. So you propose one experiment, you look at the outcome, pick the next one, and so on. Whereas in practice, you typically want to parallelize, right? You want to run many experiments in parallel, and then depending on the outcome of that batch of experiments, plan the next batch and so on. And so there's very natural ways of doing that, parallelization. So we've proposed some ways of doing so, and one can also theoretically analyze basically the potential of parallelism in Bayesian optimization. I'm very happy to talk more about that later. And now basically we can sort of synthesize batches of experiments. And so here are some experiments that they actually ran by using this algorithm. So they started with these 3 parent sequences. From those, in prior work, they had generated a library of chimeras that they evaluated exhaustively in the lab. And that already gave quite a substantial gain compared to these parent sequences. And now, given this batch, first what they did is they basically used machine learning in order to predict performance of other chimeras that they could generate. And then just they selected a new library that had highest predicted value, right? That's basically supervised learning. You fit the predictive model, you rank it according to the expected performance, and synthesize those. And while on average, those tend to do a little bit better, they weren't actually able to improve on this previous library that they had collected. So there was not sufficient novelty in the exploration. And now using basically this batch Bayesian optimization algorithm that I've described, using confidence to guide exploration, they basically generated a collection of rounds of batches. And after a number of those, they were actually able to find sequences that were substantially more stable than those that they had found in the past. And so, of course, this is now a number of years ago. I think it was the first or one of the first applications of Bayesian optimization in this context. Since then, there's been quite a lot of work, also using more modern machinery in terms of, say, deep learning for, in latent spaces and so on. But overall, this strategy is quite widely used now in this sort of context. We also talked about automatic machine learning. So I'd like to just briefly say about this. So this, as I said, an area that's quite important in industry as well. So one of my former postdocs, Daniel Golovin, went to Google and built up the Google Vizier service. So that's a service for black box optimization that's used within Google for hyperparameter tuning across a whole range of different models. So here's just a few quotes of the paper that they published at KDD a couple of years back. You can learn a lot more about implementation details. So they used as sort of default this batch Bayesian optimization algorithm I've described before, with a whole bunch of really clever extensions on how to transfer information across similar data sets and so on. So very much encourage you to read. So this is really useful. It also describes a really nice application. If you talked about sort of creativity and discovery here. So one experiment that they did is actually they used this algorithm in order to search for the most delicious chocolate chip cookie. So that experiment is described in the paper, and they also actually came to the NeurIPS conference and did some cookie tasting with the cookies that they generated. So I encourage you to take a look at this. Okay, so now this idea of using confidence to guide exploration and experimentation is much more generally useful. So that you can naturally extend this beyond individual objectives to multiple objectives. So you try to sample efficiently, explore the Pareto front. Say, for example, in this drug design setting, maybe you not just care about thermostability, but also binding affinity with respect to certain receptor molecules and so on. Right? Or in machine learning, in automatic machine learning, you not just care about validation in the training set, but other notions like fairness of the machine learning model and so on. Okay, so that's a setting where oftentimes you have multiple different objectives, and one can now basically use the predictive uncertainty to reason about plausible Pareto frontiers and guide experiments in order to become more sure about this, this multi-objective problem. Similarly, oftentimes you not just want to find one single good solution, but actually a whole range of good solutions, so enumerate local optima and so on. And there's very natural ways of encoding this. We want to impose additional preferences in terms of novelty and in terms of diversity of the solutions that you would want to find. Another very important practical aspect of this problem is that oftentimes you not just have one optimization problem, but you have many related ones, right? So in automatic machine learning, for example, you might want to find, say, the best neural network architecture for a given data set, but then, right, you probably have many different data sets, so the data set changes over time and so on, and you don't want to start the search from scratch, and you want to make use and reuse what you learned in order to do better on new tasks. And there's various different ways of doing that too. So one very recent work that's going to appear at NeurIPS this year is when we use similar ideas in these carefully calibrated confidence intervals for Gaussian process models and related models for model-based optimistic deep reinforcement learning, where we figured out a way of basically searching policies that optimize optimistic performance, so being optimistic about the unknown dynamics of the system that you're trying to control in a way that's actually computationally very tractable. And this yields very effective and very simple, efficient exploration strategies that with very few episodes of interaction with the system actually learn highly rewarding policies. Here there's some illustrations from this from the NeurIPS paper here. So this also works in situations where you have where the exploration task is very difficult. So for example, in these sort of settings, especially those if you, for example, have action penalties. So it means it makes it very difficult to find good policies. So one last topic that I want to talk a little bit about that we spending quite a bit of time thinking about is safe exploration, particularly how to deal with constraints. And let me again start with the motivating application. So this is a collaboration that we have with the Paul Scherrer Institute in Switzerland, in particular in using Bayesian optimization and reinforcement learning to tune the Swissfeld free electron laser. So the Swissfeld free electron laser is a 700-meter long linear accelerometer that creates X-ray pulses of extremely short duration, so femtosecond duration, 1/1,000,000 of a billionth of a second. So using this, you can image extremely fast processes like molecules turning into each other in the context of a chemical reaction, for example. And of course, that has many different applications from drug discovery to material design and so on. And so it's also quite a complicated machine with many literally moving parts. So basically there are, so the electrons start at the source and then they get shaped through a complicated sequence of magnets, undulators. And these magnets can really be moved around to shape the beam into different, to have different properties. And depending on how you configure these magnets, you can control the beam intensity that you get out. And now the problem is that these beam properties very subtly depend on environmental conditions, so on temperature, humidity, etc. So there's not just one parameter setting that always remains fixed, but this constantly needs to be adapted. It also depends on experimental properties, so depending on which experiments you're carrying out, you might want to have different parameter settings and so on. It's also a setting that's extremely expensive to simulate, so you can't just carry out these experiments and simulations. Because first of all, this subtle dependence on environmental conditions is very hard to simulate, and also simulations are really, really slow. So they actually have to do this search and tuning on the system online. On the other hand, you also have to make sure that you don't break the machine while doing so. So basically, if one is not careful with how to configure the beam, there can be beam losses that demagnetize the magnets, right, and basically damage the machine. And in order for that not to happen, they measure beam losses in this laser, and you have to make sure that however you calibrate this beam, these beam losses don't exceed critical levels. Okay, so now one way to think about this is to again start with our black box. Maybe in this case representing this free electron laser that we can inject some experimental parameters on, measure the reward, say beam intensity, but we now also measure how close you get to violating any of these safety constraints. And now, given those experiments, right? So the trouble is those are not known ahead of time, right? So you don't know exactly what will be the effect of different control parameters. And so you basically have to learn online. So given the experiments that you've done so far, you have to propose the next experiment that you want to carry out. And the goal is basically to solve this constraint optimization problem, right, with stochastic zero order feedback, while making sure that none of the constraints, are violated at any given point in time. So you basically have to explore this fitness landscape, this reward function, but you have to ensure that this exploration remains safe, that you don't do ever anything unsafe while you explore. And so to that end, one can make similar use of this predictive uncertainty in a way that I've described to you before. So this is this picture that we talked about a little earlier, right? But you can also make similar reasoning about the constraints. So if you now have our constraints and want to ensure that no matter where we evaluate our constraints, they remain above the safety threshold, then one way to do so is to ensure that we only sample wherever our pessimistic estimate of the constraints exceeds the safety threshold. Okay, and of course, in order for this picture to be valid, the same sort of rationale and properties need to hold that we discussed for the objective function before. So you have to make sure that these confidence intervals are actually well calibrated, so that basically the true constraints are actually contained in these confidence intervals. And now the first idea would be to say, well, let me just take a standard acquisition function like GPU-CV or expected improvement, etc., and always restrict it to this red subset of the domain where we can statistically certify safety of the experiment. The trouble with this is that typical exploration strategies, just being optimistic basically, is typically will lead to poor solutions, because very quickly the plausible maximizers shown in green, right, where the upper bound exceeds the best lower bound, are contained in the strict interior. So we would only keep doing experiments around this expected high value region and miss out on possibly much better solutions somewhere else in the space. So there's not enough incentive to expand our frontier to discover new solutions that are still safely reachable. And so one way of ensuring this is to explicitly reason about expansion. So there's an algorithm that we proposed on how to do that, that basically keeps track of experiments that we can statistically certify to be safe, as well as the set of these regularity conditions, as well as the set of plausible maximizers that we talked about before. But in addition, we now also keep track of this purple set of plausible expanders. So these are subsets of experiments that allow us plausibly to infer additional actions to be safe, right? So they allow us to expand the subset of the domain in which we can find high value solutions. And now in this case, we would keep sampling basically also these expanders and eventually actually discover that there's much better solutions on the other subset of the domain. Okay, and so now this is kind of the algorithm in the stylized description. And so one can actually, under similar regularity assumptions, that the unknown of objective constraints are members of the reproducing kernel bit space associated with the covariance function that the Gaussian process model uses, and so on, one can actually formally guarantee both safety and completeness of the resulting algorithm. And so here's the first proof of concept experiment that we've done a couple of years back. And this is basically a quadcopter that flies from A to some target location B. It starts with some initial controller that was derived from some first principles physics model, but it doesn't perfectly describe the real system, so it doesn't lead to very efficient motion. And so now what we do is we inject additional tuning parameters into this controller that we safely explore using this algorithm that I've described before. So the robot fully autonomously experiments with its own control parameters in order to discover behavior that is more effective, while at the same time making sure that at no time safety constraints are violated. And so if you use standard exploration schemes, you immediately crash the robot against the wall. So it immediately destabilizes and crashes, versus here, it safely, cautiously explores, leading to eventually improved behavior while not failing along the way. Okay, and so now, since then, there's been a number of other applications. So there's been some really nice work by Yanan Sui, who's a co-author in the SafeOp paper, and his collaborators on basically using this algorithm in the context of the application medical rehabilitation. So they use safe Bayesian optimization, so a variant of the algorithm that I've described for discovering effective treatments for spinal cord injured patients that are basically electrical stimuli applied to electron arrays, electron arrays that are implanted in those patients. There's also more work that we looked at in sort of safely tuning building controllers in order to make them more efficient and so on. So I talked about the free electron laser. So here's some results on this. So my students actually ran some experiments live on the machine, so deploying the algorithm, where they basically would start at parameter settings that our expert collaborators had manually found. They would detune adversarially those settings so that they lead to much worse behavior. And then they would use and compare different strategies with the goal of finding new configurations of this machine that hopefully work as well as those from the human expert. And in many cases, they actually were able to find settings that perform better than those that they started with. And there's also substantial improvement compared to standard so-called local search strategies that are applied sometimes in this domain. Okay, so that brings me to the end of my talk. So there is at first sort of this major challenge when using machine learning for discovery. So we really have to embrace the fact that this discovery is really an iterative process, that we'll have to sequentially collect data. And I think there's a major opportunity in using machine learning models in order to help and guide this data collection process, help exploration. Oftentimes, there's all sorts of constraints that arise in this context, such as budget constraints, safety, diversity, and so on. And to capture all of those, really careful uncertainty quantification is absolutely crucial. And I showed you some examples of this. Of course, one key challenge is where can one find such good models, right, that not just lead to good predictions, but also lead to good predictive uncertainty. And I think that's one of the major methodological challenges. Of course, for certain applications like robotics, maybe one can sometimes start with first principle models and really come up with informed prior distributions, but oftentimes really would like to discover good prior distributions from data itself. And so we've been recently spending quite a bit of time exploring ideas for meta-learning, for sort of meta-learning good prior distributions that we can then use for exploration in tasks like Bayesian optimization and reinforcement learning. And there's some work that we've done building on ideas from Pack Bayesian theory on new ways of discovering such prior distributions that actually yield very good predictive performance on real data, as well as very good calibration performance of the predictive uncertainty. Here's a few references in case you'd like to read up on some of what I've talked about in more detail. And I'd like to end by acknowledging all the students who did the work in the talk that I presented and all the senior collaborators. And it was just a lot of fun to work on this research. So thank you very much.
Thank you very much, Andreas. It's really nice the way you presented results, and I believe that many people have been reintroduced into this topic in a very nice and easy way. So it's really one of the things that also attracted, and you can see that we had more than 300 active participants throughout the talk. And so my name is Anna Androsova. I'm a senior data scientist at the Swiss Data Science Center, and I would like to take several questions from our audience. So first of all, we apologize for technical inconveniences, and right now you can go to the swap card application, follow onto the program, and then click the Keynote session. When you click on it, on the right side, there will be a live chat with the questions that you can post and use it. So we will be waiting for some questions from audience. And meanwhile, I have one question for you, Andreas, already, because it's something I'm fascinated about. And I would like to ask, what do you predict will happen in next 5 to 10 years?
Okay, so if you're working in machine learning, you know how hard it is to predict things, right? Especially the future. So I don't want to venture too far ahead in trying to make such wild predictions. I mean, clearly there is a lot of work in just deploying existing machinery in ever more applications, and that will continue, right? So we'll also see more, I mean, continue to see investments in special purpose hardware for machine learning, right? To sort of just make machine learning part of ever more systems that we encounter in our daily lives, right? And I think it sort of just gradually keeps becoming more and more invisible technology that we use more and more. And of course, so this is something, I think that's a process that is happening already, right? And I foresee will certainly continue for some time to come, right? Whether yeah, so I mean, I think that is definitely something that I think is to be expected, and of course, along with this, right, we'll have to make sure that the technology that really is deployed is really truly reliable, and I think it will also require rethinking a lot of the classical ideas that have been developed in the context of system design, software engineering, and so on, right? To just embrace machine learning as part of the overall systems that are being deployed.
So actually branching out of this question, maybe the next one, what is your take on initiatives that are currently trying to make machine learning more interpretable and more explainable? And do you think this is something that will come in more and more importance for future of the companies to be adopting the solutions?
Yeah. Sure. So I think that's a very, I mean, interesting topic, explainability, interpretability, and so on. Of course, the importance, I think, is various different aspects relating to this. So the importance, of course, clearly depends on the application. So the higher the stakes of the application, right, and the stronger the potential effects on people involved, right, the stronger, of course, the expectations are in that front. Interpretability is a little bit of a difficult topic, so it's very hard to make precise, right, and to really define, to declare success. Right, maybe one can sort of express preferences among different types of models. Maybe sort of a linear model that depends on few variables is more interpretable than a complicated black box, right? But in the end, it's something that's very hard to really make precise. So I think it's really much more important to sort of try to understand sort of how can we get away from simple, say, decisions made by a black box to sort of try to broaden and increase the bit rate between the human expert using a machine learning or AI system and the decisions that the system takes. And there's quite a bit of work happening in the community, sort of trying to gain some insight in how certain decisions have been reached by a machine learning model. I think there's lots of interesting challenges that still need to be embraced. And of course, another important issue is that there's always, of course, a trade-off, right, between predictive performance and interpretability, right? And depending on which applications we talk about, that trade-off might lean in one or the other direction.
Totally agree with you. Thank you very much. So I would like to check if we have right now new questions from the audience. And there are some. So the question is, how do companies can strategize these topics efficiently in a daily business, like machine learning for discovery or model building with constraints in mind?
So, I mean, I think it's a long process, right? This just doesn't happen from one day to the next, right? I mean, I think it's also very difficult to answer in such generality, right? So one would have to narrow down more concretely particular subject areas, right? And explore more carefully about what are the potential opportunities that machine learning can really bring, right? And I mean, I think it's a very powerful tool across a range of applications, but of course, it's not all powerful, right? And there's many tasks, right, where it might just not bring the progress that one would hope it could bring, right? So I think it requires really careful introspection and assessment, right, of what concrete value it could bring, right? And I think attending events like this one today is sort of a great way to get started, to learn about what others are doing, experiences, right? And talk to experts, places like SDSC, right, to draw on the expertise.
Thank you very much. We have one more question. Actually, can you please clarify again the formulation of safety in Bayesian optimization? It's not clear to me whether this notion of safety can be imposed on the combination of input parameters such as safe input, or is it the objective function evaluation side such as safe value for the system?
Sure. So the way I formalized the problem was basically as a constrained optimization problem, right? You're optimizing some objective function subject to certain constraints, and you want to ensure that these constraints don't exceed a certain threshold, right? So it's just a classical constrained optimization problem. And what we require is that we not just want to produce a feasible solution at the end, right, one that meets the constraints, but wherever we evaluate the objective and the constraints are satisfied, right? So all the iterates, all the experiments that are carried out must satisfy the safety constraints. So this basically means you're solving an optimization problem with both unknown objective and unknown constraints, while having to ensure that all the function evaluations remain feasible along the way, right? And so that's where the technical difficulties basically lie.
Thank you very much. I'm checking if there is, yes, so one more question. What is your take that big companies like Google, OpenAI, and alike make even bigger models which become closed business and they are not really accessible for the research community?
I mean, that is not exactly sure what you're asking me to comment on here specifically. I mean, certainly, I think it's
maybe if I would like my interpretation of the question, do you see as the industry and the research community developing in parallel, or would you see any certain point where we can intersect these developments and combine the strengths of the both, you know?
Sure. So I mean, I think in general, there's been quite a healthy collaboration between industry and academia and machine learning, and there's lots of exchange either way, right, of ideas, but also more concretely software and data to the extent it's possible, right? So, I mean, right, in terms of all sort of open source software that's been released by big companies and so on, right, that the academic community certainly is benefited from, right? And of course, industry with all the ideas and talent that came out of academia and so on. I think that's so obviously a symbiotic relationship between the two, right? And I think that's been quite healthy in the past. Of course, now when it comes to extreme computational efforts required to train big models and extreme sort of amounts of data required to train these models, at some point it just becomes very difficult for academia, right, to compete with these kinds of resources, right? And I think there's a dialogue that's needed in terms of how to facilitate collaboration even in that sort of regime, right?
Thank you very much. I see exactly what you mean, and hopefully there will be more and more fruitful collaboration and beneficial to both of the worlds. And let's, in future, hopefully we will not call it both worlds, but one machine learning big field where everyone can coexist and be benefiting. So one more time, I would like to thank you, Andreas, for this interesting discussion, and I hope you enjoyed the rest of the event. And I would like to introduce our next speaker. So Chiara Riccobene is a knowledge management officer at Math and Work, which is a spin-off from Moxoff. Chiara will present us a real-time game intelligence and how math befriends sport. Chiara?
Hi, everybody. I will now share my screen. Let's see if you see it.
Yes, everything is perfect.
So, real-time game intelligence. Let's see how it works. First of all, a short agenda. We will introduce who we are, so what we actually do in our spin-off, and then we will focus on the data, because data science, big data, it's the key word. So we have to understand really which data is involved in this theme. And then who is interested in this data? When is better to collect, and how actually to collect this data, and why, which type of analysis and which type of insight we want to retrieve from this data. Finally, how the models that we used to better exploit the data and the information that we want to retrieve. So let's start from who we are. We are a spin-off of Polytechnic of Milan. We were born in the far now 2010. We are 10 years old, and we were born actually from the dream of MOX Laboratory of mathematics department, the dream of building a bridge between research, advanced front-end research, and the industrial world. Why? Because there was, they realized that there was this gap between what they were producing as models, algorithms, and what actually was implemented and used in the industrial world. So here we are. We worked with a lot of clients, a variety of domains of applications. We are around 30 people, and we created 2 spin-off. One of them is Math and Sport. I will talk about that later. So as you can see from the core skills, we are not only focused on data science, but we also perform mathematical modeling and optimization. And we are very proud of this combination of different approaches, because we think that when we face a new problem, an issue, we should be able to choose among them and sometimes combine them. And this is the very new frontier in this field. At the end, what we like to do is to implement what we have studied and the models that we have found in an end-to-end solution. So exploiting also the data engineering and software development skills that we have in our group. As I said before, we started a spin-off in 2016, Math and Sport, that now counts around 10 people, because we started working with Italian Committee of for the Olympics, CONI, at the beginning to optimize the gesture and through videos that were tracking the action of the athletes. But then we realized there was a lot to do in math and sports, and we created Matin Sport. And we have a starry advisory board, as you can see, because it features on the bench. We have Alfio Quarteroni, is a very important professor from the scientific side at EPFL and the Polytechnic of Milan, and a principal investigator in many ERC programs. And we have from the sports side a match analyst and a volleyball coach of the high value of Adriano Bacconi and Andrea Gianni. It's not a case that we have volleyball and football. Well, we are Italian, so I don't know if you know, soccer, football is known as to be a passion for Italians, but also volleyball. And these were the two main focus that were the source interest for Matin Sport. And I will present mainly two examples on this kind of sports. But let's start from the beginning, data. So we are talking a lot about data, and sometimes, well, very often we speak of big data. It's true that there is need for a huge amount of data to let the model be trained and perform well. But actually in big data, we have also the complexity of the data. And we want to transform this buzzword into smart data. Is the travel I want you to make in this speech is to go from a big data to smart data. Let's have a look at what kind of data do we need when we work with sport. As I said before, quality matters. So we have to carefully choose which is the data that I'm exploring, and we have a big opportunity in the world of sport because we have an increasing amount and diversity of data coming from innovative and enabling technology like video tracking and other software that are tracking in real time. And these technologies are having high performances and very competitive costs. So they become even more and more available. So we have tracking data like players' positions, but we also have additional data that we don't have to forget about, like the events on the match that are the points, the cards, the substitutions, or what is changing during the match, and also the registry, the record of the players and of the team, the matches and the championship. I presented the different data set that we have in volleyball and football. As you can see on the left, you see semicolon and numbers, but this is actually a real match. So if for a scoutman, that is the man that is sitting next to the coach and is actually tracking manually a lot of information, this is a real match coming from the information of these numbers. We are quite lucky in volleyball because for the moment the position is not so important. Why? Because volleyball, I will repeat this concept a lot, is has a rigid structure for a game. It has fixed rules, 6 court zones, and you can have only 3 consecutive touches at most per team, per point. So this will help a lot in the choice of the models that we are going to use. Then you have also fixed events. The events are like service receptions, but these for the moment are tracked manually. It has been used, this kind of type of tracking for a long time in the volleyball world. So we have a lot of data, and this is a good thing. The bad side is that as there is a human being tracking this data, when it comes to the rating, so sometimes the use that we do of the coding that we use to score the action, sometimes this can vary according to the person that is taking the data. Completely different is the data set from the football. Why? Because here you can see this is a tracking position of the players on the field that is provided the real time. So this is widely adopted in these days, and it has obviously a high frequency of information, because we can have from 16 to 25 seconds frame information snapshots per second. It's a really dense information. But even though we have this information so well automated, from the other side, still we are tagging manually if, for example, the game is dead or alive, or if the possession of the ball is on the away team or on the home team. And obviously, the fact that there should be someone doing this manually during the live game or after a posteriori, it's a cost, and this causes the fact that for that the data that is stored for the historical games is sometimes lack of information. Why? Because obviously we cannot always pay a person to be on every match of every league. This is a key point because it will be the excuse to introduce machine learning, we will see later. So who is interested in this data? Well, everybody, I think, right? Obviously, coach and team, but the news is that we, with the virtual coach app and the fun app that we developed, we try to engage also the fans. Obviously, the same information has to be treated and to be elaborated in different ways, depending on who is the stakeholder and who is the end user. The coach needs to have timely alerts when he's looking at the game in real time, and he has to supervise the entire game with historical data and information of the distribution of how the game was played in the past. So the difference, for example, with the players is that they need to know which kind of situation, which kind of behaviors their adversary is used to play to be able to prevent these actions. Fans instead just want to have as much as information as they can, and this can be done using their phones and streaming the video, on which we can use augmented reality to provide them with interesting KPIs on the players and on the game. When do we need to collect the data? Well, obviously, always. So before, because we need here, yes, big data. We need a huge stock of standardized and structured data to be able to train the models and to perform and to test the algorithms before using them. And then obviously the new approach is to retrieve data also during the game. This is something that is very important, because we can actually profit from giving the opportunity to the fan, for example, to stream video and then retrieve this video to use them afterwards. But also, as I said before, during the game, you have manual tagging and other events that need to be tracked to after be able to, in real time, understand what's happening and what's the evolution of the game. Why? Obviously, we wanted to analyze, understand, classify, and predict. I will show you some examples of how we do that. And let's start from the analysis. In volleyball, one of the focus is the setter, that is the main player, that is actually the director of the game. And it's quite common that all the teams study the adversary player before playing against the adversary team. Here we have two tools, the Volley Virtual Coach and SETEX, that on the top left and top right represent some distribution of how the setter has been playing in the past, and which type of rotation will be the more profitable. Obviously, this information is not useful if we in real time do not provide also how far we are from what we expected. So it's very important to know and to analyze what's what happened in the past, but also to know now how far am I from what I learned. So warning alerts are very important only if the relevant information is different from what I expected. And here is the case, well, an example of distribution. The black line is during the game, and the green lines are the past games that have been selected to study the adversary. And the tool provides alerts when there is something different with respect of what I expected. We want also to predict what is going to happen, and obviously this is a tool for the coach. For example, always having a look at the setter if we are giving a service and we know which type of service and where, in which zone of the adversary court is going to go, then we can actually use some models to predict which is the probability of attack of the block, where to block. So this is very important to because you can imagine the field is quite big, and to place the blockers, it's very important to prevent and to know where it will be before it will happen. And obviously likely to know which is the direction of attack. With this tool, we can do that, and it's a very impressive how it is useful to the coach during the game. Sometimes it's not always that we want to have a focus on the setter, but on the whole team, especially before the game, where we want to choose which team will be the one that is going to play. And this tool, Prometeo, is done with this purpose. The focus is on all the players, and every player has a profile based on his historical data. And it simulated the entire game, given obviously the players that are going to play, the rotation, so the position of the players on the fields, and so on. During COVID lockdown, we played actually with different coaches on YouTube direct videos, where they were choosing their teams, and they were actually having a report on how the match finally ended, and not only the points that were made, but also the performances of every player. And this is very important to understand which are the synergies between different players or players against different lineups of different teams. And it helps in choosing and preventing before the match. And this simulation, as I said, it's in real time. But you cannot do a lot of things if you cannot classify the action. So this tool that was made in the football domain was made to enrich and process the data. And how it works, the data from the provider of the video tracking, in the case of the football, gives the position of the players, of the ball, and of the referee, but not always, as I said, because it's taken manually, the position of the ball, of the ball possession. So if the game is dead, if it's for the home team or for the away team. So the idea was to make a machine do the work. And we use the machine learning algorithms to decide frame by frame if the game was dead or alive, and then we use the rule-based approach to decide if the game alive was for the home team or the away team. You classify, and then you classify the action, then you can provide KPIs at different frequencies. And this is very important because obviously you can imagine especially in football, actions can be very different time frames. You can have attacks that last for minutes, and action that are only for a few seconds. Let's go to the core of the presentation, so how we are doing that. You remember the prediction in the volleyball? Well, behind the prediction of where the setter will direct the game, there are thousands of competing models. So these models are decision trees. So quite not so complex. It's an old method that has been used a lot in data mining and statistics, and it's quite clear. And it's the structure of the game helps the fact that the humans have a lot of insight on what the model is doing and which choices are made. We trained thousands of models on the historical data. Luckily, as I said before, we have a lot of data for the volleyball games, because it has been a long time since they started to track the position and the events of the game. They understood a long time ago that it was useful, and these historical matches are used to train the model. Then during the match, the nice thing about decision tree is not the decision tree itself; it's how you prune it. And the value of this approach is that we can make these models that have been trained among a cluster of hundreds of processors for more than 24 hours run on a laptop in real time, because they compete between themselves, and the ensembler, this is an algorithm that choose which of them are performing better. Action by action is varying the weight that are given to their importance, and it's just choosing the best models to predict the next action for the game that we are looking at in real time. Completely different approach, but also because the purpose is different, is for the Monte Carlo Markov chain. Again, thanks to the structure, the rigid structure of the volleyball game, we can schematize the different touches as steps in a Markov chain scheme. And this is very important, because we can use the historical data to compute the transition between an event and another. This is service, reception, set, attack. And these are always very strict, the passages between these events, the transitions, and the probabilities comes from the historical data that we have. And this is not only done for the setter, but for the entire team. One important thing is that using the Monte Carlo approach, we can simulate a lot of games, and then have an insight of the estimate of the results of the game that we choose to play. And this is quite interesting if we want to play with the data and with all the variables that are involved. That's to say, will I put a middle center blocker next to another player because I know it performs well? Well, these what-if scenarios that usually a coach can only do in his head, based on his experience, can have a quantity now that can support his decisions. The process to perform this simulation is obviously to collect information that will be used to analyze the players' behaviors and to compute the transition probabilities, and then simulate the match with the Monte Carlo method, and finally analyze the results. The example I gave you before, you can find it actually in YouTube. If you if you Google Matte Sport and Prometeo, you will find all the sessions of the game with different levels of insight on the variables that have been used and that have been added to get more and more close to the real game structure. At last, but not at least, the temporal convolutional network, it has been used in the football domain, where we have here a sequence of data, very dense, very high frequency data on a timeline, and we wanted to map this information into an output of the same size. So temporal convolutional network is perfect for that, and we don't want to lose the information that we have on the raw data itself. The raw data is obviously the player's position at every second, and the output is the ball dead, or the ball game dead or alive. So it's very easy for a human being to see that, but you will see that even among human beings, it's not so easy to classify these events frame by frame. So why temporal convolutional network? Because, well, Google did it, so maybe we thought everything Google did, we should give it a try. No, without joking, it's a very good structure architecture, and Google used it to implement his assistant talk, and which is the connection between audio, so audio streams like words and sentences and player's position. Well, the variation between a sequence of data and the time scale in a word that is in a sentence, and if you think of the variation of the small accent at the end of the word, this is the same approach that we can think in the player's position. Small variation have a great impact on different scales. So we have to conceal the information that we have in the different scales. A sentence is made of the words, and then also of the intonation, of the tone, of the accent that we use. And the same is for the player's position. The player's position at the beginning of an action will be important, or the last player position at the end of the action will be will determine the effectiveness of the action. Another thing that they have in common is the higher frequencies. We already said that we have 16/25 snapshot of position per second. So it's a lot of information that we have to handle. And obviously the fact that this is unstructured data. When you think of the position of the players on the field, and what will you see later on the video that I will show you how they actually move, you cannot imagine to force them into a nice feature matrix that we are used to know where the columns are the position, or they are ordered, and so on. So the property of being able to handle unstructured data in this case is fundamental. But why TCNs and football? Well, because first of all, usually are human beings that are the one that are analyzing the data in real time. Especially, I don't know if you have the same, but we have a lot of talk show in Italy where commenting and analyzing the game in real time. But if you think of the quantity of information that you have per second, this task is very tough. So we try to get this information directly from the raw data. And the nice thing about the neural networks is that they can preserve this information and the structure from the input until up to the output. One feature of the temporal convolutional network is that you actually, the convolution, so the hidden layers that are the convolutions are causal from the future to the past. So you don't have leakage of information. And this is very important. Another thing is that if you pre-process the data, as you usually do when you use other types of algorithms, you will lose some of the information, and sometimes the insight that you put in the pre-processing the data is biased. One way to give support to the people, to the analysts of this game, is to give them quantitatively and actually not biased, so not subjective information directly from the raw data. Some results, and then I will show you a video. We, as I said, implemented the model for the classification of dead game or a live game. We tested it against, first of all, the data that we have where this classification has been tagged during the game, so from the data provider, but also against human validation done a posteriori, so looking at the video frame by frame. The results are good, obviously, after the results of assessing if the ball possession is in the home team or in the away team are worse, but we are working on another model where we actually want to classify directly the three ball possessions. So that game, away team and a home team. Here, an example of how the human validation a posteriori and the data provider tagged the game. And so the black is that game, and away team and home team is blue and red, and how the machine learning by himself classified the different frames. So even between the human validation a posteriori and the human validation in real time, there was a difference. So I think we can provide more a good help in this classification. I want now to show you a video to end, just to show you how the virtual coach is actually working in real time, and then I think the time will be over, but let's see later. Ooh. Sorry. Ooh. Sorry again.
We can see video, but no sound.
Well, I think that I don't know if we have enough time again, but that this could give you an idea of how it works, producing relevant KPIs in real time and following the match. We were in the field, as you could hear, and the level of automation that we reached. Yeah.
Thank you, Chiara, for this interesting presentation. I think that other videos will be really interesting to be discovered by the audience during the dedicated Q&A session. Meanwhile, I would like to ask everyone not to forget to submit your Q&A, your questions to the chat, and then Chiara will take over there. So now, I would like to introduce our next speaker, who is Kean Walmsley, a software architect at the Autodesk Research in Neuchâtel. And Kean will present his research into the generative design.
Thank you, Anna. Let me go ahead, and I think if you can enable screen sharing, and then I will...
If you can try right now, please, I think.
Perfect. All right, and then let me share my desktop. But then I also want to make sure before we get moving that my computer sound comes through. Okay, I think we're good. Great, thank you very much, Hannah. All right, welcome to this session. Thank you very much to the Swiss Data Science Center for inviting me to talk. I'm not really a data scientist, so this could be interesting for people. My work at Autodesk Research, I work on two main areas of research. One is relating to building digital twins, integrating IoT data into building models, but then I also work on generative design projects, and that's what I'm going to talk to you a bit about today. So you can reach out to me through Twitter or LinkedIn. I'm Kean W. I also have a blog at keanw.com where I share quite a lot of information about research that I'm involved in, and my email address is there as well. All right, let's proceed. So I was asked to talk today about generative design. I mean, I'm actually involved in projects related to generative design on the AEC side of the space, so side of the business. So AEC for us was architecture, engineering, and construction. So I'm tending to work on projects related to those, but there was quite a lot of interest in hearing about projects that we've been working on for manufacturing customers. So I'll be talking about two on that side as well. We'll be talking about the AI chair that we've developed with Philippe Stark, and then the JPL lander that we developed in conjunction with NASA. So though I wasn't involved personally in those projects, I was involved in the projects that I'll talk about at the second half of the session. So there's quite a lot of material, so hopefully it won't be too much for people. So let's introduce generative design. So
I
yes.
don't know if this is for everyone, but I cannot hear your sound.
There is no sound yet. It's just me talking.
Okay.
Yeah, so I haven't played a video yet, so hopefully that's just fine. I just wanted to make sure it was working for later. But you can hear me, right?
Yes,
Yeah.
right.
So, okay, so that's fine. All right, thank you. So generative design, we talk about generative design as being a form of AI, which is really about helping us design, better products, buildings, infrastructure, and systems. It's really a combination of a number of techniques. So we're mostly working with genetic algorithms to explore solution spaces for designs. We're integrating increasingly machine learning, though it's not really the major focus today. We're doing more and more related to machine learning, but we're integrating a lot of computational design as a kind of a core foundational piece for that. And the idea of generative design is that it allows you to sort of generate multiple solutions for a particular design problem, but it can yield multiple sort of optimized solutions that are fully validated in advance. So that's the advantage. And so let's take a look at what that might mean related to a traditional manufacturing process, where very often when you're developing a design, you're creating a number of concepts, but during the validation step, you'll kind of iterate backwards and forwards, looking at, for a particular design, evaluating whether it meets the needs of the design, but then thinking about manufacturability. Is this design even feasible to build? And so you'll probably loop backwards and forwards a number of times related to a particular design until you find one that meets the criteria, and you go ahead and produce it. Now, with a generative process, so this is a typical part that you might generate during this with one of these processes. Now, with a generative design process, what we're really doing is asking the computer or asking, using computation to generate multiple validated manufacturable options upfront. And then it's really up to the designer after they set up the design and let computation generate various designs that could meet their needs. They will then explore these solutions and ultimately choose one that gets produced. So ultimately what we're seeing is a significant reduction in time to market in generating designs and producing them. So when let me talk about this project for the AI chair in conjunction with the Philippe Stark and with Cartel. Now, Philippe Stark is I'm sure all of you are familiar with him, but he's a designer with more than 40 years of experience. He's based in Paris. His studio delivers upwards of 200 projects a year, pretty much. At any one time, he's working on 200 projects. And these may relate to product design, to interior design, to architecture, to transportation. and even to space tourism, of all things. So, you know, there's quite a lot of variety there in terms of the projects that he's working on. Now, Philippe Starck, in terms of his design principles, you know, he's really about trying to use less material to create more efficient products, and also more human products. I mean, that's really something that is at the core of what he's trying to do. Now, he has also designed a lot of chairs, you know, upwards of you know, several, so probably several dozen mass market chair designs, of which one, the Louis Ghost chair, has sold more than 2 million, you know, copies of that chair. Now, one of the things that Philippe Starck realized as he was going through his design process is that really, you know, we are all driven by our biases. We're formatted to think about design problems in a certain way. Now, this is something that he felt he was suffering from. And so when he came to us and we described the concept of generative design to him, he was inspired to think, well, this is something that could really help go beyond my biases, go beyond my formatting, and help me do something generally creative, you know, and do the next generally creative thing that, you know, along the long list of things that he's done before. So his question to us was, you know, can generative design find a solution to support my body with the minimum material? So what we did is we took sort of his best, you know, his most popular chair designs, particularly the Louis Ghost chair there, and we went ahead and extracted the proper angles for comfort and ergonomics, and the sort of the ideal minimal surfaces from these designs. We then went ahead and took the load cases for the European standards and tests for safety and durability of furniture, and used those as a basis for the forces that we would need to support in the design that was generated. Ultimately, because, you know, this was going to be commercialized in Europe, it was always going to have to support these requirements anyway. So it made sense to take them into account when generating the design. Now here we can see where, you know, what you're seeing is a kind of a lightweighting process, or material is being removed. The blue material is the material where there's there's less stress, essentially. So we're really removing the redundant material iteratively on this particular process. This, of course, was done multiple times. Now, of course, one of the main research challenges for this particular chair was around manufacturability. You know, we're using injection molding of polypropylene to create the design. So ultimately, it was very important to have a relatively consistent wall thickness for that, because that's part of the manufacturing process for polypropylene. So we ended up with a particular result that was selected amongst the various results that were generated. Now, this was never going to be the result that was ultimately just mass produced. You know, that wasn't really the purpose. But what we did was, and also we didn't want to bias the results significantly. We didn't want to influence the results that we got back, because we knew there was going to be this post-processing step from the Starck team. So we handed over the chosen generation results to the team at Starck, and they went ahead and adjusted the form and sort of reset you know, to apply the proper ergonomics, but then also sort of introduce their signature curves, because they have a certain, you know, styling that is throughout their design, or it's part of their design language, if you like. So we went ahead, based on that, we reran the various simulations and the tests for safety and durability, and just to make sure that, of course, that the modified, slightly more aesthetic design met the you know, the requirements in the same way as the generated design did. And then it's at that point that Cartel got involved in the project. So Cartel has been working with Starck for many years, and was their sort of chosen mass production partner for this particular design. So their manufacturing engineers went and developed a workflow that would take sort of the uncontaminated production scraps from their other chairs that they're already manufacturing, and then use these as the material for this chair. So right now, this is, I think, this is the first time in Cartel's sort of 70-year history that they've been able to produce a chair which is with 100% recycled material, which is really, you know, fantastic. So it's also a very environmentally friendly chair as well. So these are the chairs. I've actually, you know, recently bought a couple. I didn't get an employee discount, very unfortunately. I just had to go onto Fista, the Fista website and order them. So you can buy them from various retailers here in Switzerland or abroad as well. I'm looking forward to getting mine delivered. There's a little bit of a wait list for them. Okay, but that's it for the chair. Now the next session, rather than talking about it myself, because it was really a project that was delivered by my projects, I managed to track down a video that I think will be useful to describe how the project proceeded. And this is the JPL lander project that we did with NASA. So I'll go ahead and play that. And Anna, please let me know if the audio doesn't come through. Okay.
The search for life in the solar system is expanding beyond Mars to the outer planets like Saturn and Jupiter and their moons. We really require greater and greater amounts of fuel to propel us into those areas of space.
Spacecraft are some of the highest performing and best engineered things that humans have ever designed. The way we're going to reach farther out into the solar system, the way that we're going to find life if it's out there, is by using better and better technologies.
Every bit of mass that you can save on the launch vehicle means you can put more scientific instruments on board.
For every 2 pounds saved on the structure of the lander, almost 1 ton is saved in the launch vehicle. It gives us an opportunity to answer one of the hardest questions of our lifetime, which is there life outside of this planet?
The goal of this project has really been to reduce mass and enable the lander to go further and further into space.
We've been working very closely with NASA's Jet Propulsion Laboratory to explore new concepts in how we can design interplanetary landers. What's really exciting about this project is this is the biggest and the most complex thing that's ever been done in generative design.
Initially, the engagement was somewhat of a curiosity in terms of research for them. They were excited about potential 10% mass savings. That's on the order of what they can do. Everyone was surprised when we were able to demonstrate 30–35% mass savings. That really opened up a whole new range of possibilities.
This lander, this whole assembly, really pushes generative design to the very, very limits of what it's capable of. We're working with JPL to really develop the tools of the future.
Traditionally in design, you would go through a manual process of identifying your components, identify where the components are located, and then building structure around that. With generative design, we identify the critical pieces and locate them so we can actually optimize for, say, packing a payload.
For this kind of structure, the benefits that generative design provides are not simply about weight saving. They also allow engineers to much more quickly iterate on the design process. It allows the design to be more flexible and for introducing more design intent into the problem definition.
With generative design, it gets to open up your mind. You start looking at these problems saying, wow, that's a really interesting way to do that. Now I got to figure out how to manufacture it.
You can see examples of generative design in additive, in subtractive, and also in casting. The ability to really leverage that problem definition up front allows us to do a plethora of design options rather than just reduce one design down to its most optimal form.
Applying these new generative design technologies to such a high performance and important problem is something that's tremendously exciting, and it's going to be these technologies that let us get out there.
We've really pushed the limits of mass reduction, and that's significantly magnified when you think of how much fuel or how much more science we can fit into that lander. The things we're working on today at Autodesk can really inspire in that search for life beyond our Earth.
Oops, let me move on. All right, great. So that was pretty cool. Now let's move on to the architecture, engineering, construction side of the house. As I said, this is where I spend most of my time. Now, the technology stack is a little bit different in terms of the way we solve problems for AEC. It's less about solving the problems for a manufactured product that somehow needs to have the topology optimized, and it's a bit more general purpose in terms of the way it's been implemented. So we start from this basis where you have a loop, which is the traditional kind of generative design loop, where you have you generate a particular design, it gets evaluated based on a number of metrics or fitness functions, and then you evolve the design process or tweak the input parameters to the model via a genetic algorithm in order to generate more results. Now, typically we use NSGA2 in order to do this, but of course that's just one choice, So what this really means is we have a parametric model that's typically implemented using a tool such as Dynamo, which is a visual scripting environment, and it has a number of input parameters, and within the core of the graph, it's doing there's creation of geometry, and then there's evaluation of that geometry using perhaps some type of simulation or other things, and then ultimately you have a number of numeric outputs, and it's the optimization process that will continually tweak the inputs to the model, measure the outputs, and then decide in which direction it should continue to search for the more interesting solutions. Now, the first project I wanted to talk about on this side, on the AC side, is related to Mars. Now, very confusingly, this is not the planet. Okay, we just talked about the JPL lander for NASA, which was related to exploration of the planet. Mars is the medical and related sciences area of Toronto, and it's actually the largest urban high-tech incubator in North America. So it's pretty significant. It's in downtown Toronto, and we have a new office there. And as it was already our showcase office in Toronto, we wanted to actually generatively design it and see if we could, eat our own dog food or drink our own champagne, and see whether the technology that we've been talking about was viable to lay out a complete office space. So we started by surveying and analyzing the prior office space that we had in Toronto. So speaking to the employees and understanding their desires for a new space, analyzing their conditions that they had in the previous space. We went ahead and received a number of various constraints. Well, constraints for the design problem were, of course, the floor plan itself in terms of the overall layout. We weren't going to increase the size of the building. But we had requirements from HR in terms of the number of meeting rooms. So first of all, the number of people that we had to seat inside this office. But then from facilities, we had various meeting rooms, various social spaces, etc., that we had to accommodate as well. In terms of assessing each design, we came up with 6 different metrics that would assess the quality of each design. So first of all, people at their desks should not be distracted, whether it's audibly or visually by their colleagues. Adjacency preference. Some people had a preference in terms of being close to certain areas or certain other teams, which we wanted to take into account. So we were matching against employee survey data as well. So data that had been collected from the employees. Interconnectivity. Now this is interesting in the sense it's about maximizing what we think of as buzz, which is having these serendipitous encounters between people in the office. Now, in the kind of a post-COVID world, that's not such a good thing. We're probably wanting to minimize buzz and minimize the passageways that people will be going along and bumping into other people. So things have flipped a little bit since we did this project, but generative design can also take into account, minimizing these things as well. It isn't just about maximizing them. We did daylight analysis, we did views to outside, and then obviously taking into account people's work style preference, whether they liked noisy environments or quiet, dark environments, etc., etc. So we generated a number of solutions. You know, at its core, our algorithm would split the floor plan into neighborhoods and then allocate amenity blocks and desks into those neighborhoods. And then each of these designs would get scored across these various metrics that would implemented in order to find the sort of highest performing designs. So this is an overall video. There's no audio on this one, but so I'll talk over it, which describes the project and how it was done. So there's a little bit of repetition in terms of what we've seen already. You know, constraints of the building, what we needed in terms of the meeting rooms and social spaces, etc. And then the goals themselves. So we can see a little bit in terms of how these have been implemented. So adjacency and work style were really about, you know, surveying what people required from their workspace. Once again, we see this idea of a generate, evaluate, evolve loop. We'll talk more about the exploration step in a little bit, which is very important in a generative design system. Now, to generate the geometry, obviously we would go ahead and split the floor plan into zones, and then the neighborhood creation is based on the inputs to the graph. So we'd adjust the neighborhoods very slightly based on the inputs, and then allocate the amenity clusters as well as the desks, and then go ahead and assess those based on the various metrics. So the geometric system would generate, you know, potentially thousands of different design options. And then the algorithms measured each of these options. So we have adjacency, minimizing the travel distance between various teams and the amenities that they want to use. We had the work style preference, which is the suitability of each neighborhood for the preferences that team had expressed around light and acoustic levels. Buzz, once again, is around you know, connectivity, or you know, this idea of serendipitous encounters and having some energy in the office. And then productivity is about minimizing visual and audio distraction for people when they're sat at their desks. So here we're looking at sort of a daylight analysis, of course, which we also did. And then we have the views to the outside to allow people to have at least have a view to a window from each of their seat. And then there's the evolution step, which would search through the design space and find the interesting solutions. And here we get into the exploration environment, which really allows people to compare, or allow the designers to compare various metrics. Sort of typically would map 4 dimensions into a 2D space. So you'd have an X and Y axis, and then of course color and size for the scatter plot. And this allowed us to really work through the various design alternatives, explore the trade-offs between different metrics, and then choose a final design to be developed. And this is the design that was ultimately chosen and further developed. So let's take a very quick look at this. Now, there's some interesting things about the design that was developed, and let's look at them here. So this goes back to what we talked about with Philippe Starck and this idea of overcoming biases in formatting that we have in designers. So there's a few things here that really don't look quite right. You know, the orthogonality is not there. It doesn't look as if it had been designed by a person, because you wouldn't typically put these things at the angles that they're at. But there was an algorithmic benefit to doing so. You know, there's something that was driven by the data, and this design performed better than other designs. Now here as well, there's a gap that's been left here, which perhaps wouldn't have been done, but ultimately this reduces, increases adjacency. So there's a lot of things that were slightly counterintuitive for people, but made sense when you looked at the data. It also, so let's take just a few quick images of the space. It doesn't feel like a very traditional office. There are some, some of the angles are a little bit different. Constructability would have been a bit of a challenge, I think. So if we'd taken that into account in terms of a metric, then perhaps this design would not have scored as highly. But ultimately, we wanted something that was provocative and interesting. Now here, you can actually see the results of the daylight analysis has been painted on the walls, which is pretty cool. So this is some more images of the space in general that was laid out. And here you can see once again, you know, a lot of non-orthogonal angles, etc. So it's an interesting space. So we're quite happy with the results. Now, very quickly to wrap up, I think I still have a few minutes left, given the delays that there were, hopefully. Anna, you'll tell me if I don't, is the last project relates to a construction company we worked with who came to us. Let me just actually play this quickly.
Van Wijnen is a construction company. It's located in the Netherlands. It's a big construction company who doesn't only focus on building houses, but is also caring about the human needs of the residents. So in 2014, Peter and Hilbrand
there should be sound. Sorry,
discovered generative
right.
design.
Well, if there is no
during
sound, then I'll just skip the video. It's really not a problem, but basically I'll talk about the project itself. So in this project, Van Wijnen really wanted to take the principles they'd seen from us related to architectural scale, generative design, and see if they were applicable at the urban scale. So they took a project that they had at the Alkmaar space in the Netherlands, and here they have modular housing. So this is something that was very beneficial to us and actually made it very easy to do. We had some constraints for the space in terms of what the requirements were. The goals for the design were a little bit different. So we had 7 goals instead of the 6 that we had for the architectural project. So here we're looking at the size of backyards, the views from the space, solar gain. So we're checking how much solar gain would get from essentially the buildings with panels on the roofs, financial metrics like profit and cost, and then the program and variety metrics as well. Now, these were then, once again, I think, is that the end of that one? So we generated a whole load of designs, of course, for this using the parametric model that we developed for them. And then ultimately, once again, provided some sort of exploration interface, which allowed them to explore the data, or allowed us to, because it was more of a study initially, we explored the data and went ahead and extracted the designs that were interested to develop further. So we went ahead and chose 3 designs, of which one of them we ultimately refined into the design that they chose for this particular site. So that is the end, I think. So I think hopefully we're more or less on time, considering the slight delay that we had due to the interruption. Just a quick recap. So today I talked about generative design very quickly. So I know that you'll probably have questions that we'll go ahead and deal with in the Q&A session. But we talked about the AI chair for Philippe Stark. We talked about the NASA JPL lander, as well as the architectural layout for the Mars office, or the Autodesk Toronto office, and then the generative urban design project that we did for Van Wijnen. And if you have any further questions, so there's a link there that may be of use, and please feel free to reach out to me if you have any follow-up questions.
Thank you, Kean, for the presentation. Apologies again for the technical issues. And I have been mistaken regarding the sound, because on Zoom, it actually was not projecting. So I think this would be a very interesting for you to continue with the video that you wanted to show in the end, because actually people can hear and explore more the projects you talked about. We will resume SDSC-Connect with a presentation from Shao Min Tan, the Senior Machine Learning and NLP Engineer at eProva. Shao Min will tell us about data-driven invention using machine learning to help create the products of tomorrow. The floor is yours.
Thanks very much, Anna, and thanks to the Swiss Data Science Center for inviting me. Let me just share my screen. Can I confirm that you can see the slides?
Perfect, everything works.
Okay, great. So as Anna has said, my name is Shao Min, and I'm a machine learning engineer at iProva. And I'll be talking about data-driven invention, or how we can use machine learning to help us create the products of tomorrow. So let me start by giving a brief introduction to iProva. We are a company based in Switzerland and UK with about 30 employees, and we specialize in creating inventions using data-driven techniques. And these inventions are created on behalf of our customers, who are usually technology companies like Panasonic, Philips, and Sony. So here's an outline of the talk. I'll start by describing how traditional invention works and some of the limitations with this traditional method of invention. And then I'll describe how using a data-driven approach can improve the process of invention. And I'll explain how this data-driven invention process works at iProva. And finally, I'll give a couple of examples of inventions that were created using this approach. So, how does traditional invention work? You have an inventor. This is a person with some amount of existing knowledge of the world and of the state of technology in the world. And one day the inventor chances upon some new information. So this could be by reading something in a book or reading something in a journal, or maybe the inventor is having coffee with a friend and the friend mentions something new that the inventor has not heard of before. And this new piece of information sparks an idea in the inventor's brain for a new invention. So this new invention could be, for example, a new type of device or a new service which nobody else has created before. And for something to qualify as an invention, we require that it be novel. So it has to be the first time somebody is doing it. It's usually surprising because if it's too obvious, somebody else would have thought of it. And it also has to be valuable. So it has to be useful to us in some way. And if you look at this process of invention, you'll see that it depends upon three things. So the first is that there's an element of chance because the inventor comes across the new piece of information by chance. And then the second is that usually the inventor needs to have quite a large amount of existing knowledge, at least in his or her particular field, because they need this knowledge to know how to use the new piece of information in order to create a new thing. And finally, all of this has to happen at the right time. So what do I mean by happening at the right time? Throughout history, there have been some examples of inventions that were created before the world was ready for them. So one example of an invention before its time was the analytical engine, which was designed by Charles Babbage in the 1830s. And the analytical engine was basically a mechanical general purpose computer. So it was able to make all kinds of different calculations, and it was programmable. So you could make it do different things based on the different inputs that you put in. And the sort of logical structure underlying the design of the analytical engine was in fact very similar to the logical structure of modern day computers. So even though Babbage spent many years designing this engine, he never managed to build a complete working prototype of it. And part of the reason for this was because at the time, given the manufacturing technology, it was very difficult to create the parts to the correct level of precision that was required. So it wasn't until about 100 years later that the first general purpose computer was successfully built, except that it used electronic components instead of mechanical parts. And that was what made it feasible. So this is an example of an invention that was created when the state of technology at the time was not yet ready for it to be realized. So there's another way to illustrate the idea that there is a right time for inventing something. And that is the many examples in history of inventions that were created at the same time by independent inventors. And one very famous example of this is calculus, which was developed by Newton and Leibniz separately in the 17th century. Another example is the telegraph, which was invented independently in the UK and the US in the same year. And for a 20th century example, we have the jet engine, which was invented in the UK and Germany around the same time. So what these examples of simultaneous independent invention show is this idea that invention is inevitable, which means that given that the state of technology of the world has progressed to a certain state, so the state of technology as well as the social structure and so on, all the pieces necessary for an invention already exist in the world, and they're only waiting for somebody to come along and put the pieces together and create a new thing out of them. So if you don't do it, somebody else will come along and do it. Now, of course, from the point of view of an inventor or a business, you want to be the first person to put together all the pieces and create the invention, because the first person to patent something is the one who gets the rights to it. So it's no good being the second to try to patent something. So as an inventor, you have to keep abreast of all of the new technological developments and market trends and social trends and so on, so that you know what the new things are that you can put together to form a new invention as quickly as possible. So given this process of invention that I've just described, there are a few limitations to it. The first is that it relies on serendipity, because there is an element of chance, and it depends on whether you chance across a new piece of information or not. So when time is of essence, this is not ideal. And second is what we call the limited breadth and speed of information reveal. As I mentioned, you need to keep abreast of all the new developments. And this is difficult because there's only so much that one person can read in a day. And it's, in fact, basically impossible to keep abreast of all new developments in all of the fields in the world. And this brings us to the third limitation, which is specialization. So many researchers and engineers nowadays, most of them are very highly specialized, which they need to be in order to contribute to their respective fields. But this means that they might miss new developments occurring in a different domain from the one that they are working in, even if the new developments are relevant or potentially relevant to their field of interest. So all of these limitations could be addressed as usual by using some kind of artificial intelligence. And this is where data-driven invention comes in. Data-driven invention has several advantages over the traditional approach. The first is that it's systematic. So instead of relying on chance, the process of invention instead becomes more robust and reliable. And data-driven invention is also fast because computers can read articles much faster than humans can. So they're able to detect new developments as they arise and allow us to make use of them quickly. And it's also more diverse because, once again, since computers can read so many articles, they're able to search for information from different sources and different domains. And so they can find unexpected connections that somebody who's working in only one field might not have thought of. And finally, the particular approach to data-driven invention that iProver does is additive, which means that it complements the R&D efforts of our customer companies. So how does data-driven invention work at iProver? We start by doing some real-time document crawling. So we scan the internet for new articles as they are published. And these could be science blogs or press releases from universities or scientific papers or white papers and so on. And then these documents go into our machine learning and natural language processing pipeline. So these machine learning algorithms could, for example, be used to create a model of the area of interest of a particular invention project. Or we could use them to do what we call invention logic, which is identifying and detecting the components that make up a good invention. And we can do this by using techniques, for example, text classification, topic modeling, question answering, knowledge graphs, and so on. And the output of these machine learning models is what we call invention triggers, which are pieces of information that are interesting or novel and that can spark ideas. And then we present these invention triggers to our in-house inventors. So these are people who have a background in physics or engineering, and they are able to use these invention triggers to come up with ideas and create inventions out of them. And then finally, we present the inventions to our customers, and the customers can choose which inventions they want to accept. And out of these inventions that they accept, they then go through the process of patenting them, and they also develop products out of them. So now I'm going to go into more detail on some of the machine learning and natural language processing tasks that we use for invention. So as I mentioned, we are interested in finding these things called invention triggers, which are interesting or new or surprising pieces of information that have the potential to spark an idea in a person. And one example of a type of invention trigger could be a new piece of research or a new scientific discovery. So for example, in this sentence, which says, scientists have created a new algorithm which enables a single drone to herd a flock of birds away from a designated airspace. So this is a sentence that describes a new piece of research that has been created by scientists. And this type of trigger is useful for us because it gives us an idea of the new technological and scientific developments that have just arisen. A second type of trigger is a surprising combination of two or more distant domains. So for example, this sentence, ingestible origami robot made of meat can crawl into your stomach and heal wounds. So in this sentence, you have origami, which is an art form. You have robotics, which is a very high-tech kind of computery thing. You have meat, which is a food, and healing stomach wounds, which is medicine. So you have these four different topics that are all very different coming together into one sentence, which makes it very intriguing. And it makes you think about all kinds of different possibilities. Another type of invention trigger could be an ability of some object. For example, gallium droplets could one day be used to power robot muscles. So this is an ability that's quite interesting that gallium droplets are able to do. And finally, we're also interested in problems. Like in the sentence, LiDAR sensors on an autonomous vehicle could damage the cameras on other vehicles. So this is a potential problem that could be caused by the LiDAR sensors on a vehicle. And the reason we're interested in problems is because inventions are often a way to solve some particular problem. So if we know about a new problem that has recently arisen, we can think about how to solve the problem and in the process create a new invention. So all of these different kinds of triggers are things that we are interested in presenting to our inventors in-house. And these are the things that we have, we create machine learning models in order to detect in text. Another kind of thing we're interested in is the analysis of trends. So if you look at this plot, this is a graph of the number of times that the word blockchain was mentioned in the literature over the past 10 years or so. And you'll see that it was first mentioned around 2013. And after that, there was a little bit of it being mentioned, but it was kind of flat. And then it suddenly exploded in 2017 and peaked around 2017 or 2018. So this kind of trend is interesting for us because it gives us an indication of what could be the new big field that's coming up. And if you plot another trend line superimposed on this, so this is an orange trend line that was calculated based on the blue trend line of the mentions of the word blockchain. And the orange trend line tells us the probability of inventive novelty of an invention in the field of blockchain. So what this means is that if you were to make an invention in the field of blockchain, how likely it is that this invention or this idea would be novel. And what the trend line is telling us is that this time, indicated by the green shaded area, is the best time to make an invention. So in fact, the best time to create an invention in the field of blockchain is, well, right immediately after it was first mentioned in the literature. And you want to create these inventions as soon as possible. If you wait until 2017 or 18, when everybody is talking about blockchain, you see that the probability that you get a new invention is quite low, because by that time, lots of people have been working on it and probably somebody else has thought of this idea that you have. So it's important for you to act as quickly as possible when a new field is coming up. So what we do is we detect these small fluctuations that come about right at the beginning of when a new field is just coming up. And of course, that's quite tricky because there's not that much data at that point in time. Now, previously, I was talking about invention triggers that consisted of single pieces of information. But we are also interested in exploring the links between different concepts or different domains, because we want to know how different pieces of information can come together to create an invention. And one example of doing this is in finding analogies. An analogy is an idea or a technique that is used in a particular field or a particular system, and then you take it and you apply it to a different domain. So analogies have usually been very useful in invention and in creativity in general. So one example of this is the concept of sound waves. So the ancient Greeks were the first to come up with the idea that maybe sound travels in wave form. And they got this idea from looking at water. So if you look at the surface of a pond, if you throw a pebble into the pond, you'll see these ripples moving outwards from the central point where the pebble entered. So you have these water waves going outwards. And the Greeks thought, well, maybe sound behaves in the same way. So maybe there are waves in the air that come out from the source of the sound. And it turns out they were right about this. So they used the system of water and water waves as an analogy for sound in order to come up with this idea. Another example of analogies used in inventions is in the first aircraft that was designed, or the first few. So the Wright brothers, when they were designing the steering system for their aircraft, got the idea of how to steer the plane by looking at the steering system of a bicycle. So in this case, they used a bicycle as an analogy for an airplane. So how do we use all this in the context of data-driven invention? What we are interested in is detecting analogies in the text data that we have. So let's say, for example, that you are working in the field of human-computer interfaces, and you happen to know that when somebody is silently talking to themselves in the head, or if they're reading something, for example, then their throat vibrates according to the words that they are saying silently. And you think, well, that could be pretty useful. So if we could detect the vibrations of this person's throat, then we could guess what they're saying to themselves, even though we can't actually hear anything. And what we can do then is that we can look into the database and find analogous systems which detect very small motions. So the software goes into the system and it finds this sentence that says, Eulerian video magnification is a technique that can amplify small motions in a video that are otherwise imperceptible. So in other words, here we have a mathematical algorithm that can look at a video, and if there's a very small periodic motion in the video, it's able to amplify it and allow you to detect it. So you think, we can use this as a method of detecting the vibrations of somebody's throat when they're talking to themselves. So we can take a video of the person's throat and we can apply this technique. So this is an example of using an analogous system, which in this case is in the field of computer video algorithms, and applying it to the field of interest, which is in human-computer interactions. So if you look at the blue highlighted sections of these two sentences, which are the two parts of the sentences that are matching, you see that they're phrased quite differently. So there's no exact match between these two. So one of the tricky things of detecting analogies is to be able to extract the meanings of parts of sentences and compare them without actually having exact keyword matches. So over the course of the years that iProva has spent creating inventions using data-driven methods, we've built up quite a large amount of data which relates to the invention process. So we know the kinds of components that make up a good invention, and we know the kinds of things that help a human during the creative process. And I've talked about some of these kinds of inventive signals in the previous slides. So we have machine learning and natural language processing algorithms that search for these inventive signals in the amount of text data that we have. And usually these machine learning algorithms that we use are a combination of open source algorithms as well as custom in-house ones that we developed ourselves. And the advantage of using open source algorithms is that these models are usually trained on huge data sets, so very large corpuses of text, and they are thus able to understand a lot about the way human language works. So for example, you have language models that understand the grammatical structure of the English language, and they understand what all the different words in the English language mean. So we can make use of the power of these models, and then on top of them, we can build our custom models, which are trained on our own in-house datasets. And the combination of this allows us to perform the custom task of detecting inventive signals. So these machine learning models are run on new articles every day as they are published, which means that if something was discovered yesterday, we know about it today, and we can invent with it today immediately. And this is good because this allows us to create inventions very quickly using the latest information that's available. Right, so let me give a couple of example inventions. The first is a user interface for smartphones using corneal imaging. And this was a project that was done in the area of the smartphone user experience. So this invention was based on two triggers. The first is a technique called corneal imaging. And this technique is based on the fact that when a person is photographed, you can use reflections in this person's cornea to show you parts of the scene that are outside the camera's field of view. So for example, you can see reflected in the person's cornea, the person who was standing behind the camera and taking the photo. The second trigger, which is more of a trend, is that the front-facing cameras on smartphones nowadays are getting increasingly high in resolution. And this is important because for the corneal imaging technique to work, you have to have quite a high resolution image. And it's only about now that the front-facing cameras on smartphones are getting high enough in terms of resolution. So the invention is this. When the person is using their phone, they are looking at the phone. So reflected in their cornea is the phone as well as their hands and their fingers. So you can use the selfie camera of the smartphone to image the reflection in the user's cornea, which allows the smartphone to see the user's hands and so detect any gestures that are made by the user's hands. And this gives us an alternative user interface to control the phone. So for example, if the touch screen doesn't work, if the person is wearing gloves, maybe, you could use this method instead to control the phone. Or if in some future iteration of a phone, you want to get rid of the touch screen because you want to save on cost, then instead you could use corneal imaging as a method for user interface. So this is an example of an invention where we use an invention trigger that came from a different domain and applied it to the domain of interest. So in this case, the trigger of the corneal imaging technique was first mentioned in the context of forensics. So the idea was that if, for example, a criminal took a picture of their victim, then the criminal could be reflected in the cornea of the victim. And so you could use this to detect crimes. And instead, we took it and applied it to the field of smartphone user interfaces. So this was a new development that probably people working in the area of smartphone user interfaces might not have known about if not for the machine learning algorithms that presented it to them. The second example invention I'm going to talk about is the autonomous vehicle passenger health check. And the project area of this invention was in autonomous vehicles and the kinds of services that you can derive from them. So the invention depends on the fact that autonomous vehicles, or AVs, have very precise control over their motion. So this means that as the vehicle is driving along, it can induce very small but measurable variations in its motion in order to generate forces on its passengers. And we can use these small forces to carry out health checks. So by measuring how the person reacts to the stimulus of being jerked around a little bit, you can evaluate their balance and their core stability. And this is good as a way of detecting the early symptoms of some diseases like multiple sclerosis or Parkinson's disease or diabetes. So this is another example of an invention which brings together two different domains, in this case, autonomous vehicles and healthcare. And it's a particularly neat invention because it makes use of the components that are already in an autonomous vehicle, so the sensors and the very precise motion control, and it uses them to do something completely different from what they were designed to do. So this makes the invention more feasible to put into practice. And that was two example inventions. And in total, iProver has created several thousand inventions so far, out of which about 500 of them have finished going through the process of getting patents filed and granted. And the patents that were based on iProver inventions have been cited by all 10 of the world's largest tech companies, including Amazon, Apple, and IBM. And also iProver is expanding its business model. So instead of just providing inventions to our customers, we're also providing the data-driven invention approach as well as the software that we have. So we recently launched, together with BIC, a data-driven invention lab. And this is a lab that's based within BIC, which uses iProver's machine learning software and iProver's data-driven invention technology to create inventions for the BIC company. Right, so that's the end of the talk, and I look forward to hearing any questions you may have later.
Many thanks for the insights you have shared with us, Shao Min. We will gladly discuss all the questions during the dedicated Q&A session at 2 p.m. Thank you very much.
Thank you.
So if I can ask to unshare the slide and the screen, please. And up next, our next speaker is Julien Hazemann, who is a computer-aided drug design expert at the Idorsia Pharmaceuticals. Julien will tackle the question, can deep learning help to design a new drug? Julien?
Hello, everyone. So I'll try to share my screen right now. Okay.
We don't see your video.
So there we go. Can you see it in full screen mode?
Yes, we can see the presentation, but your video is off.
There we go. So, hello everyone. So I'm really excited to be here today with you. I will be presenting this following topic: can deep learning help design a new drug? So here's a quick overview of what I'll be covering in my presentation today. Firstly, I will start with why do we need deep learning in drug discovery? Then how can deep learning help designing a new drug? And finally, what are the deep learning applications in drug discovery at Idorsia, my company? So let's start with why. Why deep learning in drug discovery? So the drug development process is a very long process. It takes on average 12.5 years to develop a new drug. It's also a very unsuccessful process. As you can see, more than 86% of all drug development programs lead to failure. And the cost is on average 1.3 billion for a new drug to develop. So here, there is clearly a need for new technologies. And then that's why we hope that deep learning can really help to reduce these lead times and increase productivity. My focus today will be on the drug discovery part. As you can see here, let me put the laser pointer. And this part takes more than 4 years to actually explore the chemical space, find new molecules, optimize molecules. So there will be a lot of molecules synthesized until one molecule can be used as a candidate to enter the drug development process. And still, there will be many years until this molecule might be approved. So as I said, we need to first explore the drug chemical space. And this chemical space is huge, and it has been estimated to 10 to the 60 molecules. It's so enormous that, of course, we cannot just explore it with simple methods. And here again, we might need deep learning to better explore this chemical space. Just to give you an example, so currently with let's say the current techniques, we can certainly explore 10 to the 10, which represent still nothing compared to this huge chemical space. So really, again, the hope is that by using deep learning, we can really better explore this chemical space. So on my next slide, I would like to introduce the drug discovery process and to explain our daily work to deliver a clinical candidate, so a candidate to become a new drug. So it starts with generally a target of interest. So this is generally a protein and we want to find molecules that has an effect on this protein. And of course, this protein is associated with a disease of interest. And in general, what we do, we screen a compound library. So it's a huge library of molecules, like hundreds of thousands of molecules that we physically screen in a lab on cells containing this protein of interest. And we try to identify a biological activity. And then the molecules that represent this biological activity are then called hits. They are starting point for our drug discovery programs. And then these hits are further profiled in molecular modeling, where we try to understand how these molecules behave in 3 dimensions in the protein, and we try to understand how it behaves, what are the key interactions, and so that it can help the chemist to better synthesize some new molecules that are similar to these hits. And the medicinal chemist, while they synthesize these molecules, they need to address many properties at the same time. because a drug, to be a good drug, needs to be certainly orally available, needs to go to your body, to be distributed, needs to be soluble in your stomach, needs to go through your membrane in your intestines. It needs to be safe. So a chemist has a huge challenge to tackle all of these parameters at the same time. And as you can see, this is an iterative process. So this is why it takes quite some time, because it's a trial and error process. The chemist has to synthesize many molecules. Then he gets these molecules measured on different properties. Then he gets data back. Then he is optimizing the molecules by synthesizing new molecules, and so on and so on. So you see these iterative cycles until the molecule, after more than four years, is fulfilling all the criteria to be the candidate for the drug development and enter in the clinical phase where we actually test the molecule in humans. And again, so why deep learning? Because as we can see, it's a very long process, many molecules to synthesize, very costly. So we really think that deep learning can help at many stages of this drug discovery process. So by identifying new hits, by helping the molecular modelers to better understand the interactions between the molecules and the protein, but also helping the medicinal chemist to make a prediction on the reaction to better synthesize the molecules, and also on the different properties, so we can make prediction on the properties to also guide the chemist in the synthesis, and overall to have this the deep learning in a de novo design fashion at the center of this iterative process to really generate new molecules using deep learning and tackle all of these parameters at the same time. And today, my focus will be on two aspects. So first, the identification of new starting point, of new hits. And the second aspect will be this de novo design approach. So, but let's start with now the identification of new hits. So as I explained before, so we are facing a big challenge with a large set of molecules. So generally what we can screen in a lab currently using high throughput screening. This is what I explained before, using some robotic system to screen a screening library of compounds. It's generally up to max 1 million compounds. But of course, the chemical space is huge. And then there we can also use a deep learning approach to virtually explore this chemical space and find the needle in the haystack that could be of interest. And at this point, a hit, it's still a needle because it's not yet the golden nugget. So we will need, of course, to optimize this needle to make it a good drug. So of course, as I explained before, so the chemist will have to make this hit soluble, so also orally available, so that these molecules can go through your body and be absorbed through your stomach and your intestines and reach your bloodstream and different organs. It has to also to be safe, and you have to make sure that the metabolites from the liver are safe. And at some point, it has also to be eliminated. So again, it's a lot of different parameters that a chemist needs to address. And you see how tired this poor chemist is. So he has a new idea, basically, to synthesize that he will synthesize. And generally, when he is able to solve a problem, then another problem is popping out. So again, there we think that deep learning can help us to solve this multi-parameter problems at the same time. So now let's see how can deep learning help in designing a new drug. So you might all know this feature from your smartphone. So when you type in some new words and you see a recurrent neural network is actually making some proposals, some prediction actually on the next words to be continued. So, and we are going to use actually this approach, these techniques in chemistry. But of course, we will need to, because this is working very well for text, for a sequence of character. So we will have to convert our molecule into a string, into a sequence of character. And there is a very suitable format for that, which is called SMILES. And the SMILES format is, as you can see, is a sequence of characters. So any molecules can be converted into a SMILES. And then we can use these SMILES in this natural language processing approach and make a generation of new molecules. So here's an example. So it works with recurrent neural network, and more especially with LSTM, so long short-term memory network. And we have pre-trained this network with a large set of molecules, let's say millions of molecules, so that the network knows how to generate molecules. And just as an example, a simple example, it works the following way. So we start with a seed, a random seed. Here it's a carbon atom, an aromatic carbon atom, which is converted into a one-hot vector. And this one-hot vector and then is submitted to this first hidden state. And the hidden state will output a probability distribution over the next symbol. And then this next symbol is converted into this symbol, and this next symbol is used as an input for the next hidden state, and so on and so on. And what is interesting with LSTM is that it remembers what were the previous characters, so that it can really make a prediction on molecules, on the next character, and then to finalize a complex molecules. And it works really well. So we can then use this LSTM model, so what we call a deep generative model, to generate molecules. And then what is very interesting there, we can use it in a de novo design approach, where we generate molecules, and then we can also use different machine learning models to make prediction on the properties of interest. As I explained before, we have many properties to tackle at the same time. So we can then make prediction on these properties, also on the bio activity on the target. And then we can score these molecules based on this prediction and use the best molecule to retrain our deep generative model. And what we can see is over the cycle, the course of this iteration, we get better and better. So the deep generative model is able to generate more and more of these molecules fulfilling all the interesting criteria. So it's really interesting, and you will see two showcases later where we use these approaches. As I mentioned, so we also do property prediction, and now I'd like to show you how we can make this property prediction. On this next slide, as you might know, machine learning can be explained by this simple equation, where y is the prediction, f is the prediction function, and x is the feature that you need as input for your model. In our case, it's a molecular feature, so we need to convert our molecule into something meaningful for the neural network. And one successful approach is using a graph convolutional neural network to actually keep the graph representation of the molecule into the network. And then in that case, the nodes are actually our atoms, and then all the links between the nodes are the bond, like it is in a molecule. And so all the nodes or atoms are converted into a one-hot vector, and they are stored with this little envelope as represented here. And then, we will also have the information about the type of bonds, can be a single, or double, or even triple bond. And each node is going to pull the information of the neighboring atom. And by pulling the information of the neighboring atom, it will also extract information about the bond type. And this is done, of course, simultaneously from all the neighboring atom. And then a new vector then is calculated, and that would be itself and the sum of the neighboring atoms. And this is done simultaneously for all of the atom with the radius of 1, then a radius of 2, and so on, until we get to a vector, and that's representing this graph molecule, this graph representation of our molecules. And this can be used in a final hidden layer to make property predictions. And overall, so we have developed a machine learning drug design platform where we use our internal data as a brain food to generate different models. So the generative models to generate molecules, but also models to make property predictions. So we can then use this in a de novo design fashion to generate molecules fulfilling many properties. And then we can then submit those molecules to a chemist, and then the chemist can synthesize those molecules. And then the synthesized molecules are tested against different properties of interest. And then this is generating new data, and we can use this new data to improve our models. So the goal here is really to speed up the system and to get to better molecule faster, and to finally get to an interesting clinical candidate. So now let's see what are the possible deep learning applications we are using at Idorsia. So I will show you two different approaches. First is the identification of new starting points, so new hits against SARS-CoV-2, so the virus responsible for this main disease that we are facing now. So across all coronaviruses, there is one enzyme, and it's called MPRO. And the rationale there is we want to target this enzyme because it's really consistent between across all coronaviruses. So that's why we thought that here finding an inhibitors would be really interesting, because even if a new coronavirus would come in the coming years, this approach would be also suitable. So the idea there is to find or to start from known compounds. So we looked in the literature to find some compounds that are some effects with this enzyme, We use our machine learning drug design platform to generate molecules, and then the idea is to identify new hits, and I will explain in my next slide how this is working exactly. So again, as I said, so we started with a list of molecules that we scouted from literature, and then we retrained our deep generative model with this list of molecules. So we generated many molecules. We did a bit of filtering so that we could come to molecules more suitable for our drug-like space. We also evaluated these molecules against our enzyme of interest, so this MPRO, as I explained. And then the best molecules were used to explore the enamine real space. So the real space is a chemical space of 14 billion molecules that are synthetically accessible. This space is actually offered by a CRO based in Ukraine, and this company is capable of synthesizing those molecules. So we explored this space and identified some analogs molecules, and then again we evaluated those molecules against our target of interest, and we then finally scored them. And then we retrain our deep generative model and generate new molecules. So in this iterative process to get to better molecules after a few iterations. And then we could identify 33 molecules from this real space, and then we ordered them at enamine. And as you can see on this next slide, we could identify one hit. It might feel a bit not much from you, but actually for you, sorry, but actually it's quite good, because we ended up with a hit rate of 3%, and as comparison with the standard approach using high throughput screening, this is what we generally use in pharma industries. So it involves a large robotic system, also huge store to store our screening collection. And then there we use a lot of consumables to screen our screening collection. And in general, the hit rate there is around 0.1%. So it's here a great achievement by using deep learning. So we really think that this approach is very interesting, and we will now, of course, continue and we'll try to identify even more hits using this approach. On the next slide, this is another project where we optimized molecules using the same machine learning drug design platform. It was a CNS project. That means we had to target brain, so CNS for central nervous system. So the target is in the brain, and here the goal was to generate molecules by playing on this 3 point of derivatization, sorry, and also to optimize on these properties just there. So what we did, so we used the chemical series from this project. We retrained our deep generative model to generate similar molecules, and we filtered them. We used machine learning to make prediction on the different properties. We also assessed those molecules against our target of interest, and we scored them and used again deep generative model to generate new molecules. And again, so after a few iterations, we could really see that the deep generative model was able to generate more and more of the molecules fulfilling all the criteria in terms of properties, but also in terms of affinity towards our target. So we could then and select molecules. So 50 actually molecules were selected and synthesized. And we already have partial results where we can see that here, out of those 50 molecules, for 18 of them, we have already data on 3 properties. And if you compare these molecules from this machine learning drug design approach with the molecule from chemistry, we can see that we have a huge enrichment toward the right properties. So again, it's a great success here, and we are now using these techniques more and more in different projects. So now that I covered the 3 sections, I'd like to close with answering the main question of this presentation: can deep learning help design a new drug? And also address some additional takeaways from our own experience regarding these machine learning projects. So can deep learning help design a new drug? I would say definitely yes, as deep learning can help identify new starting points in drug discovery project. And as we can see also, it can help to optimize molecules in this multiple properties that we have seen before. But of course, we certainly need a very good communication between the chemist and the data scientist. And I think this is really key for the success. So the data scientists really need to understand the scientific challenges, and they also certainly need to manage expectations, because what we have realized is that some chemists are really resistant towards the technology, and some were, on the contrary, very, or maybe too optimistic, thinking that the technology will solve all of their issues. So we really need to somehow educate the stakeholders so that they can understand the benefit, but also the limitation of the technology. Also, what we realized is that the machine learning or deep learning itself cannot do much. It needs to be associated with or integrated with other computational chemistry approach, and then you can really get to better outcomes. And finally, of course, there is still room for improvement. So we really believe that in the future, with more data and maybe better descriptors, then we will be able to deliver better models. So I'll be happy to then, that's the end of my presentation, sorry. I will be happy to answer some of your questions during the Q&A session starting very soon, I guess.
Thank you very much, Julien, for presentation. Thank you. So now I invite everyone to the dedicated Q&A session. After the Q&A and afternoon break, stay tuned for the panel discussion that will be followed by the keynote presentation. And as a small demo, to answer multiple questions for the morning session, I would like to navigate on how to follow the links. I just need to ask for the support to enable my screen sharing. All right, so I guess while we wait for the technical help, meanwhile, if you go onto the swap card, there is one of the tabs that is called Live Discussions. Clicking on the Live Discussions, on the left side, you will see Q&A deep learning or Q&A data-driven discussions. And I right now can be sharing the screen. So Here I am at the SDSC-Connect. After the program, you can see we have live discussion, and clicking on one of the sessions below, you can follow the links to join the Zoom and have a fruitful discussion with the speakers. Thank you very much, everyone, and let's recommence in a very short time.
Good afternoon, everybody. Welcome to the panel session, which is going to start soon. I would like to share some slides as a support for the session. Today, we are going to continue along the string of very interesting talks regarding creativity and discovery supported or assisted by AI, by focusing right now on aspects related to the societal impact of these technologies. And to do so, I have the pleasure to welcome our panelists who are very well-known people in the Swiss AI world. The first invited panelist is Christine Chichester, who co-heads the digital lab at Firmenich, which is one of the largest companies when it comes to fragrance and flavor. We then have Nicolas Henchoz, who is a former TV news anchorman and now the director of the EPFL ECAL Lab, which is a very interesting laboratory hosted by the Cantonal School for Arts of Lausanne, but is a spin-off of EPFL. Cristina Kadar, who is both a member, a senior scientist, a senior data scientist at NZZ, Neue Zürcher Zeitung, so one of the most prestigious Swiss newspapers, and also a member of the Media Technology Center at ETH. And finally, Marie-Valentine Florin, who is a member, the director actually, of the International Risk Governance Center at EPFL. So welcome to the panelists. I hope you can now use your microphone to intervene in the talk. Maybe to kick off this panel, I would like to invite Christine to tell us a bit more about the relationship between AI and consumer products. And most notably, I would personally have a few questions for her. Christine, can you hear me all right?
Yes. Yeah, sure, no problem. I can hear you quite well. Perfect.
Excellent. So, yeah, I guess, I mean, some things that I'm quite curious about are, in general, what are the uses of AI and machine learning in the world of fragrance and flavor? Because I guess some of us have heard news about fragrance that is created by an artificial intelligence. Maybe if it's possible for you to give us a bit more detail about this, especially with respect to what's happening at your company in this area, more generally the area of creative AI. And also, of course, if you can share of any developments in the public domain, I guess many of the attendees of the panel would be more than happy to hear about these.
Yeah, thank you for inviting me. It's been a great conference so far. And I'm only a little bit sad that we're not interacting in real life to get to talk about these things during the break, but maybe next year. We'll, let's see. Yeah, so just a little bit about the background of AI in flavors and fragrances. In fact, this is an industry, a consumer industry that's been using a lot of AI these days. And it's becoming a really a data-driven, innovative sort of aspect for us. In this industry, we create flavors and fragrances, and as well as molecules. But that's let me go into that a little bit in a minute. But the idea when we create a flavor, a fragrance, or a fragrance, it is a list of ingredients with a quantity. So it's kind of like a recipe, right? And we know in this area, there's been a lot of work creating new recipes. We had Chef Watson, right, who is able to create new recipes, building on all the recipes out there on the internet. There in the flavor industry, there's quite a few things happening where people create new. I just saw yesterday, in fact, there was a company based in Lucerne, Switzerland, that has developed a new AI. They call it an AI beer. We have another company in that has made an AI whiskey, for instance. And what this means is that they figure out how to use their recipes or their formulas that were made for these flavors and to recreate them in an AI way. In the fragrance side of the industry, there's a lot going on as well. I mean, one of the other biggest flavor houses is also working on this, and they've been able to create a fragrance in Brazil made by AI that was it was with a collaboration between IBM and Bonicio, where they were able to create an AI flavor or AI fragrance and even put it on the market. And it's been quite successful, as I've heard. So there's a lot of innovation in this area because of the matrix that we start out with, which is like a recipe. So we have a lot of ways to apply different AI techniques, machine learning, to either create or optimize. On our side in Firmenich, we've been using these techniques to do all these things as well: create, optimize fragrances for specific attributes, like either how strong it is, or how sustainable it is, how to use the most sustainable ingredients to create the fragrance. This is one thing Firmenich is really passionate about, is creating sustainable, eco-friendly fragrances. And this is one of the things that we put a lot of effort into. So we've been able to use AI and some machine learning to build up our fragrances in the most eco-sustainable way.
Very interesting.
And then there's also the point about we've done that as well as we've used AI, and this is something that comes to the point that you made about the things in the public domain. We are also using AI to understand how molecules smell. It's somewhat like the last speaker who was from pharma, who talked about their process to generate hits in pharma. Well, our industry is based on chemicals and natural ingredients as well, and we need to create these new chemicals that have new smells and new odors, new tastes to use in our recipes or in our formula. So we've been using AI for that. And in fact, today we do have a crowd AI challenge out there to help us try to understand how molecules smell. Last year, Google put out a paper on some GNNs to predict the odor of different molecules, and we have assembled a data set of molecules with their tags, with their attributes, their olfactive descriptive attributes. And we have put this up as an AI challenge where we're hoping a lot of people can come and participate and help us improve some of the algorithms that we need that can predict smells for different molecules. So there is actually a lot of things going on in the whole industry, and all of it has to do with trying to make AI in a creative way, because in our industry, when a perfumer, for instance, creates a fragrance, they often think of themselves as an artist in a way, either like a composer who is creating music, or even an architect who's trying to, set up a building in the right way, or even that it's a storytelling type of artistry. So with all these types of analogies, you can see how that involves a lot of emotion. So we need to also as well incorporate emotion into our AI. So how people really feel about this. How do we incorporate consumer attributes and consumer knowledge to make the best formula for a fragrance or a flavor? So there's a lot of things going on in this area, and it's moving quite quickly, and it's really exciting, and especially to see these things coming out on the market as well.
Thank you. That's very interesting insight. So if I understand correctly, there's a sort of competition for teaching machines to smell molecules?
Yes, so this is available at AICrowd.org. It's a crowdsourcing type of platform where people, it's like a Kaggle kind of platform. And we put up a challenge there where we are trying to find the best algorithms that can determine how molecules smell. It's very similar to the question that was posed in a paper from Google in 2019, last year. And they proposed a method for determining using graph neural networks to determine how molecules smell. And we've added a data set that people can play with and try to come up with the best algorithm for this. And there's prize money, and this is something that's in the public domain.
Yes, and indeed that paper created quite the buzz, at least in the specialized, let's say, community.
Most
Perhaps,
definitely.
Thank you very much, Christine. Perhaps one thing that I would like to mention as well is that, of course, we have a lot of specialized press which is dealing with AI in all its forms, but there is still, in my opinion, a challenge that resides with the media in communicating about AI and its creative potential. I am not sure that it's so well known already, for example, that you can indeed teach a machine not only to read and to see and to hear, but also to smell and maybe to even touch. So I would like to ask Cristina, who is from a media company and the Media Technology Center, if she can comment on indeed the media's role in communicating about AI in general and about AI and creativity in particular. And conversely, perhaps if you can also tell us how your company or media companies in general can benefit from AI in the task of creating and discovering and selecting content that they can then publish.
Hello, can you see and hear me?
Definitely.
Okay, great. Great to be here. Very interesting questions. We can start with the first one, although it's not my area of expertise, maybe my own opinion on what would be the media's role, right, in communicating about AI. In my opinion, it all starts with education. And in this case, also with journalists taking time to understand not only the potential dangers of AI, but simply also the basics of some of these techniques and also their limitations, but beyond all the hype. And then take the time to transmit this knowledge further to their readers. And I don't know, this could be partially achieved by having them maybe partially trained in the domain or partner with some experts. And a simple example for us that we did at NZZ, once we launched our recommender system, it was very important for us to transparently communicate to the readers how the technology works. So I wrote an article on NZZ am Sonntag together with one of our editors, explaining in lay terms how this works, well, basically, yeah, trying to get users to familiarize themselves with the algorithm. And if we were now to talk about the second question, right? So what is the benefit of AI for media companies? I mean, there are so many examples out there. I can maybe focus on some that I know best from my daily job. And we could start with the use case of discovering content for the users. So yeah, the most ubiquitous example there is recommender systems. that are used to surface and to filter information for the users. And for example, the news outlets, they could use recommender systems to surface content that the user might have missed, and or then the content might be of interest to them based on their reading history. But this is only one way to actually design recommender systems. You could design a recommender system also the other way around, and recommend actually articles that are further away from your usual reading preferences. So outside of the topics you usually are interested in, or even outside of your political inclination. So I don't know, think of a surprise me feature that would then surface news that are outside of your usual sphere. And then we can yes.
This is very interesting because on social media, oftentimes you tend to have the remark that you get a recommendation for what you already like, and it's very unlikely to be recommended with content that is not that you will not appreciate, let's say.
Mm-hmm.
So
Mm-hmm.
having this kind of surprise me feature for an objective news outlet would definitely be something that I personally would very much enjoy.
Yes, exactly. So you could definitely have different recommenders with different purposes by design. And you use the same technology, just basically optimizing for a different output. And another maybe very interesting technology that's out there right now, reaching maturity, would be maybe stance detection. So let's say you have a stream of news from one outlet, or potentially even more outlets, and you would automatically first maybe summarize and cluster the news in topics, and then you could run stance detection algorithms that would basically then within each topic identify articles that are against a certain issue and then articles that are supporting a certain issue. Examples, I don't know, from the US, pro or against abortion, or from Europe, pro or against nuclear power, right? And then you could basically then present to the users then this topic, and then the different streams of opinion within a topic. It's another very exciting, I think, technology that could be applied to news.
And maybe coming to your particular newspaper, which is the Swiss German newspaper,
Mm-hmm.
how applicable would these techniques be already in the reality of the types of text that you
Mm-hmm.
would be selecting and generating?
Yeah, so we definitely have already news recommendations that have been deployed for some years already in the different data products, either on the front page or on the apps for both titles. At the moment, we do indeed more content-based recommendations. But another use case that comes into mind now, thinking about the creating part, right? So we talk now only about the distribution. How can we use their automatic techniques? But also in the creation part, there are now newspapers that have done, including us, first steps in automating simple articles, but with very maybe rich visual content using established data sources. So automatically generating live results of sports events or of polls or of elections. And this frees up journalists for writing more deeper analysis pieces, right? Which one can argue is a benefit for everyone, for the company and also for the society at large. And then there are other, but still we are here in the early days, there might be other ways not to automatically produce content, but to help an author produce it, right? So find a suitable title, or find a suitable teaser picture given a text, or even, maybe a specific scene in case of a video that could be used for a preview. And here you have, again, certain layers of different layers of technology, from simple A/B testing to maybe do some semantic search. So I don't know, use deep learning to do scene understanding, and then basically find, based on the content, right, that you're interested, relevant scenes, relevant pictures or scenes in a video, or even going further, which is still probably in the academic research world, not yet so much applied, could be even understanding emotions or understanding aesthetically pleasant scenes in a video or in a collection of pictures, and then use those.
Thank you very much, Cristina. Indeed, I very much appreciate the idea that artificial intelligence and machine learning can act as a support technology in order to free up humans to do what they can do best. Indeed, I guess this is kind of related to the topic that is in the back of everybody's mind, which is deep fakes, right? So on the one hand, perhaps recommending content which is not too much trivialization or generalization of concepts, which would therefore result into actually a false, ill-derived recommendation, if you like. And on the other hand, the problem that is wading through the mass of content which is generated automatically, which is actually not correct, which is fake. And maybe regarding this topic, I believe it would be interesting to hear from Marie-Valentine, because Marie-Valentine has quite an extensive view on the governance aspect and maybe what we could call the flip side of creativity. I mean, the too much creativity, which has been created on purpose, or maybe not so much on purpose. So for Marie-Valentine, I guess I would have in general the question of what are the problems that are posed by deep fakes, and beyond deep fakes, which is probably the tip of the iceberg, what the media knows about, is there actually a taxonomy of risks that are related to machine learning, and particularly with an eye to Switzerland? I mean, are deep fakes the main governance issue there? Are there other issues related to machine learning governance which are more pressing?
Yes, so thank you. Thank you very much for the introduction and also for inviting me. I'm very much afraid I'm probably going to look like the bad guy in this conference because yes, indeed, I'm going to talk about deepfake. That is the deliberate creation or manipulation of video, text, or audio for the purpose of causing prejudice. And so the malevolent here use the fact that those that create these deepfakes want to create prejudice to others is what worries us in this trend. It is, as we know, deepfake is used. I mean, is illustrated by video, but not only. You can also use deepfake to generate images, audio, and text. GPT-3, for example, in text is booming, and there are really very much there is a lot of concern there. So it is indeed a problem because these techniques are used by malicious actors, and they have access very easily to these new capabilities, and they can deploy cyber disinformation and reputational attacks. It's not only easy, it's also very cheap and very powerful. And these visual attacks, these visual threats can indeed present serious risks to individuals, to brands, and to organizations. And I'm going to try to share my screen to show you some of the trends where you're going to see that it's so now we have the trend is really steep. From 8,000 or roughly deepfake videos online in December 2018 to 24,000 in December last year, and almost 50,000 in June this year. And also the concerns raised because it's much more sophisticated, much more difficult to recognize and to see the difference between authentic video and fake video. And there are, in fact, relatively few public examples of harm. So that's the good side of it, you know, of harm that can cause significant damage to people's reputation, except, for example, except typically in pornography, where it seems that to be still the field where the majority of video are published and disseminated. According to Sensity, which is this young and small organization which changed its name recently from Deep Trace, most targeted countries are the US, with about 50% of online video deepfaked, UK and South Korea with 10% each, and India and Japan with about 5% each. And the most targeted sectors are entertainment, 63%, mainly on Instagram, Twitch and YouTube, fashion industry with 22%, and then politics, business and sport with 40%. And overall, it's mostly public figures more than organizations. So concretely, what we see is that individuals are impersonated in pornographic video, which represent, I think, about 90% of deepfakes available online. Politicians, especially in the US and some other countries like India, are portrayed saying things that they never said. And people in these countries are generally unable to see the difference. So this is actually a threat to democracy and trusted institutions. In Switzerland, what can I say for Switzerland? I think that Switzerland is probably less affected, and well, it's certainly actually less affected, and probably because of the relatively high level of political or moral conscience, you know, and responsible behavior and digital education. So what we see is 3 types of damage: reputational damage, financial damage, and manipulation of decision making. And for each damage, the impact can be at the level of individual, at the level of an organization, or at the societal level. The individual damage, the most frequent examples are when a person's face or body is swapped into a fabricated video. And here the deepfakes are possible instruments of individual intimidation, coercion, or defamation. And this can actually be very serious when it leads to erosion of norms of what is true, you know, what is fundamentally true, you know, and what is wrong. And another example is when deepfake can be used to undermine audio and video in court cases. It has been shown, for example, in the US that a lot of courts are not equipped to detect deepfake, nor even aware that they can be shown video proof that may be faked. At the level of organizations, insurance claims could be manipulated, as well as financial markets. But I guess here I would say it's possible that many organizations are relatively well equipped to deal with fraud and cyber attacks. And what would be more of a concern for them would be reputational damage. And finally, at the societal level, we should worry about electoral manipulation in a country like the US these days, or deliberate stoking of tension or panic or conflict, and perhaps, you know, something quite maybe weird, but impact of transgression as an end in itself. You know, people who do this just for fun. And so, what can we do? Well, there is a range of response strategies. Strategies can be on the technology side, can be on the risk management side, can be in terms of law and regulation and governance. And I'm not going to go into the detail, but on the technology, I'm sure you know that we continue and we need to continue to do work and research into techniques to distinguish between authentic and fabricated video. And there's work being done at EPFL and a related startup. On provenance, it consists of techniques to verify the origin and the integrity of a video. internet platforms such as Facebook, Twitter, or YouTube should probably intervene more to influence the way people and algorithms share digital content. On the side of risk management, well, what we need to know is actually to know better who is impacted. We need more granular risk assessment. And there are many voices who claim that reporting incidents would be a good way of in the end, trying to prevent and avoid some of the negative impacts of deepfakes. Law and regulation, we need legal guidance. For example, even the question of whether the European GDPR, the Global Data Protection Regulation, applies is not clear. There are different aspects that need to be considered, and it's not enough that we say, yes, it applies. No, we need to know why it applies, and we need to prove that there is harm, and that's the problem. Hard law is needed, but hard law in this type of domains, it's very difficult to make it implementable and enforceable. So it's not obvious. And there is one thing I'd like to mention, because it's very often the case in countries that it blocks from proper regulation, is the right to free speech. And in particular in the US, for example, the First Amendment, that is the right to free speech, makes it unclear whether a ban on convincing video forgeries would be constitutional. And that's really big of a problem. Soft law would help as well. I'm not going to go in details there, because this is what Facebook and Twitter have published, decided recently about whether and how they sort of flag, tag, or remove deepfake videos. And finally, society, well, there is education, of course. Education is not a panacea, but it's needed. And educating the public about how to spot deepfake is useful. And I think that Microsoft has a project there. And finally, digital governance, and this is your question, Cristina. Deepfakes prompt wider questions about internet governance, platform governance, platform regulation, including the prevailing incentive structures and business models. So governance is needed, but the problem, and I won't spend much time on that, but the question is actually society itself finds it hard to know what it wants. And deepfakes highlights fundamentally the importance of fostering trust in the digital world, and that's something very difficult to enhance.
Definitely. Well, thanks very much. The Citizen Center being an educational platform, I really find it interesting that your contribution and Christina's contribution were focusing on this educational component of being aware of, first of all, what is possible, and also, of course, of the threats of technology posed by technology. And I think, I personally think that the education...
We must educate, of course, but we must not throw the baby with the bathwater. And that's something that is very difficult, and we must emphasize, balancing the beneficial use from the malevolent use. And education is really at the core of that.
Yeah, I perfectly agree. And indeed, there is the negative note, of course, of being aware of deepfake, and there is the positive note of being aware of the opportunity that artificial intelligence creates, which is definitely something that should be communicated more upon. And perhaps on this cue, I would like to turn to Nicolas Henchoz. I would really like you to tell us a bit more about the creative component of AI and its role in society, because definitely we are used to measuring AI performance in terms of objective, quantitative parameters in a technical way, but the EPFL Ecolab is there to remind us that creativity is also about societal impact, cultural context, and emotion. And therefore, how is it possible to contribute consider that contribution, the contribution of the artistic dimension in the realm of AI? Can you comment about this?
Yes, thank you very much. And for me, it's not only to remind you this, but we try to find solutions for this. So I'll try to share you some picture to go very fast around some of this issue that we're dealing with. So first, we are Design Research Lab, where we belong to EPFL, but we're based into the ICAL, the University of Art and Design in Lausanne here. And what we try is really to see how we can turn technical performance into acceptance, into adoption, how we can create meaning out of this technology. We have designers, we have engineers, but we have also psychologists to measure the impact, because often we have cool ideas, but at the end, the outcome perhaps doesn't work as we think. So when we speak about this involvement between creativity, we often think about art, and it's true that AI is involved in art. And you can go, for instance, on the proceedings of the last SIGGRAPH conference. I was part of the jury this year, and there was a lot of contribution of AI. And see, I can show you some work. So it's AI to create artwork itself. It's quite popular right now. One of the famous work, for instance, it's a Memo Acten creation. He's quite well known because he's a kind of rock star attitude, look. So, yes. but he has also some interesting points when you, for instance, transform very rough picture, as you see, into landscape. So it's not just an aesthetic play. It's also trying to have us to rethink how we consider the vision, what we see behind the picture, what's the source of the picture, and these kind of things. But it's interesting work, but it's really developing creativity in a certain way. But what is interesting is when you look at this visual performance, is to think of some of the issue. First, usually AI, it's based on a huge number of data. So it's trained on old stuff. So you can say, okay, but the artist himself is also trained on old stuff because he was raised in culture, and it's also with his neuron trained on old stuff. But we are still a bit trapped with the AI on the data that exists, which is not a bad thing, but you must just be aware on that. Often in our domain, because we're dealing also, so it's a bias because we're dealing mostly with visual things, and I know that there's also a lot in sound, but it's often about the visual effect, or the form is, you play with the form rather often with the content itself. And the biggest thing is that the AI doesn't bring the intention. So it's interesting to see how AI can push the creativity, how can bring and combine different things. And what we saw, for instance, the fragrance is you have so many components that a human couldn't play with all this richness. So AI had to play with such a richness, but will not replace the intention of the artist and this part of the creation. That's where you see the complementarity between the artwork, the creativity, and of the human side, and what the machine can bring. Then there's another side. It's really AI to create user experience. That's where design, and we're mostly working on design. So use the artistic thinking, but to prepare something that is useful for people at large scale in the daily life. And here there's plenty also of use. We can play around shapes, find new solutions. And here again, AI is a tool to help the designer to find new solutions in complex problems. And we ourselves, we bring, and that comes back to the media issue here. For instance, it's an installation where we try to immerse the user and bring different sources of information. That was an experiment with the Swiss television, where we bring a different source of information from the television, from Instagram, from other sources, and we're able to combine this in a global experience. And only AI help us to analyze the different picture because they have different indexation. So we couldn't do this by hand with such a mass of information. So it enrich the context, it enrich the content, and it brings new type of experience. So it's a really fantastic tool to help creation, for instance, of heritage. But what is interesting is we have to face new challenge. When you're dealing with this, it's probabilistic tool. So you cannot be 100% accurate. And usually when we think about the deep fake and this kind of thing, we think about the bad people intentionally sending bad news, or wrong news. But when you combine, if you don't combine absolutely accurately the thing, you also you induce non-intentional fake news or inaccurate news. And this threatens a bit the trust that people have, because normally for people, it's the machine must be
when the machine does something, it's always the same result. It's almost perfect, and we're used to this. And here we have to face a machine that is behaving a bit differently, that offer a lot of possibilities. So we need to see how we can, at the same time, use this AI, because it really brings an additional capacity, but at the same time, keep and even increase the trust. So you have the transparency, but when you open the transparency, and we did a huge study here with different partners around this issue, you also bring some complex notions of probabilistic approach, and people are a bit lost. So it's not easy to keep the trust of the user. And eventually you need to understand what's the meaning of the experience. And when we come back to the user experience, I will just give you, to finish, one example is, sometimes when you have a new tool like AI, it's like, this sentence, when you have a hammer, you look at each things like a nail. And here it's a bit the danger. So one of the work that we did a couple of years ago, it was with Karl Aberer's lab and Sciences Po Paris. In a big conference, when you have 30,000 people, you have a lot of information coming out in this conference. And the people in the conference, they don't know what's really happening in the different rooms, in the different discussions, and they need to know this, but they're a little bit lost. So you have strong analysis like Sciences Po Paris, but that takes really a lot of time to understand over many years who are the main actors, who is doing what. That's one thing. But when you're in real time during the conference, then you go to this kind of figures where you try to extract the position of the different actors through the tweets and different semantic analysis, and then you extract the arguments and even the opinions. And so we try to see how we can, show this in a better way with our designers and our engineers to make it, useful for the people. And it was a nightmare. We couldn't find a solution to bring this in an easy way. Until we stopped to work just with this tool, and we went one step back and say, how it is really useful. It's for the people when they're at the conference, when they're at the cafeteria discussing with another person. So they need to have something in their hand, on their hand phone. So we need to rethink not big clouds of points, but have something very simple with 2D diagrams and be able to compare these diagrams with just the gesture of a thumb. And so we had to reconsider really the whole user experience, not only the tool itself and what we can do with the tool, and go back to something very simple and that could be implemented in a 2D interface. Behind this easy interface, you have all the complexity of AI. So just to show you that, I think it's very impressive how AI can bring and push the creativity, open new perspective, but we must not be trapped by the AI itself. Consider this as a tool and make also a step back, see now how we can make more sense out of it in our daily life, what's our perception, and how we can induce adoption if we don't want to have the Google Glass syndrome at the end. So you have a perfect, fantastic tool, but at the end, it goes nowhere because you don't have the adoption by the end user. So that's how we consider, and I would say the design world more this issue of AI, which is really useful, and we use it a lot.
This is remarkable. I mean, I think it gives a very good understanding of the human in the loop component of the learning process. I mean, one thing is really coming up with technological innovation and opportunity, and one thing is seizing that opportunity in a way that makes the most impact. I would like to remind the attendees that the upcoming keynote will mention a lot more in the direction of creative machines. And with this, I would like to thank our panelists for their very interesting insights. I hope you can stick around for the keynote, and also through the swap card application. I hope you can receive our attendees' questions that we didn't have an opportunity to ask during the session. Thank you very much.
Thank you.
Thank you very much.
And we continue our afternoon with a keynote speaker, Arthur A.I. Miller, the author of many critically acclaimed books, including the Pulitzer Prize-nominated book, Einstein, Picasso, Space, Times, and the Beauty That Causes Havoc, Insights of Genius, Imagery, and Creativity in Science and Art, and Colliding Worlds, how cutting-edge science is redefining contemporary art. He is currently Emeritus Professor of the History and Philosophy of Science at the University College London. His book on AI and creativity in art, literature and music, called The Artist and the Machine, The World of AI-Powered Creativity, will be published on November 10th in the paperback edition. And this book is the basis for his presentation today. Author, the stage is yours.
Thank you, Anna, for your very generous introduction, and I thank you all for attending, however vicariously. I shall now split my screen, okay. Okay, knock, knock. Who's there? Alec. Alec who? I like knock, knock jokes. Well, that's rather lame, but I'll bet not many of you guessed that that joke was created by a machine. Now, creativity has always been a controversial topic, and especially in the age of AI, where it has been extended from humans to machines. And this is what I will be discussing today. All singing, all dancing, machines that make art, machines that make music. Said otherwise, creativity in humans and machines. Now, there has already been glimpses of creativity in machines when running algorithms like Deep Dream that create bizarre images that were hitherto unimaginable, AlphaGo that plays championship Go, generative adversarial networks that generate images and assess them too, and creative adversarial networks that create new art styles. Now, more about these exotic creatures later. For now, I ask, how do we move on from here? How can we create or evolve even more creative machines? To do so, we need to understand precisely what we mean by creativity in terms that are applicable to humans as well as to machines. Now, many people think that the notion of machine creativity is an oxymoron, because how can something made up of wires and transistors be as creative as an Einstein, a Picasso, a Shakespeare, a Bach, or a Beethoven? Yet we are merely an amalgam of veins, arteries, bones, muscles, and cells, yet we manage to be creative. The great question is, what makes us creative? How can new concepts emerge from those already established in the brain? How can a system, be it a human or a machine, come up with a product that goes way beyond the material it has to work with? Now, my own theory of creativity evolved from emerged from my studies of highly creative individuals. And I've been led to define creativity as the production of new knowledge or artifacts from what already exists. This is accomplished by problem solving. And indicators of the creativity and the new knowledge or the artifact is given by whether it is surprising, novel, complex, or ambiguous. Very subjective categories which must be handled with care. So the end product of creativity is an idea or object that has never been seen before. And the process by which it is achieved is problem solving. Now, scientists solve problems, that's easy, but so do artists, musicians, and writers. And it is the process of problem solving that sparks their creativity. What more can we say about the process of creativity? Well, in 1908, the French mathematician, scientist, philosopher, and keen observer of creativity, Henri Poincaré, suggested a four-stage model for problem solving. There is a conscious thought stage where researchers sit at their desks and work on a problem. They will undoubtedly get stuck. The experienced researcher will take time off, but that's only conscious time off. The intense, passionate desire to solve a problem keeps it alive in the unconscious, where it can be turned in ways that are not existent in conscious thought, owing to barriers and that exist there. So it is hopefully along these lines that the solution or illumination emerges, which then percolates up into consciousness for the fourth or verification stage, which is a very important phase because solutions to problems don't emerge in full form, in golden shiny form. Rough edges must be honed off, deduction sought. Now we ask, what are the dynamics of creativity? What drives the process? What is the sine qua non of creativity? My studies of highly creative individuals have led me to suggest, and these emerge from those studies, I call them characteristics of creativity, and among them are inspiration, suffering, introspection, imagination, and a high degree of competitiveness. We're reminded here of Steve Jobs' audacious theft of a revolutionary computer interface invented at Xerox Corporation. Then there's unpredictability, being out there, having worldly experiences, like falling in love. And then there's problem discovery and finding connections between apparently disparate concepts. Now, many of you will have noticed that there is an emotive dimension to many of these characteristics. And we know that the mixture of emotions and unpredictability can be explosive and trigger the new idea. For example, the Viennese physicist Erwin Schrödinger sought for some months to discover the equation that would bear his name in quantum physics. Lo and behold, he discovered it in the course of a passionate, illicit weekend with a paramour. Now, I will return to how machines can possess human characteristics of creativity and so be creative like us. But for now, enough theory. Let's turn to a case of creativity. I want to talk about how Alexander Mordvintsev created the algorithm Deep Dream. Here is Mordvintsev and myself at last year's highly prestigious Lumen Competition Arts Exhibition in London, where I served as judge for AI-created art. Now, Deep Dream was the first algorithm that allowed artificial neural networks to create stunning new art. And the creation narrative that I will now discuss comes straight from an interview I did with Mordvintsev, and I was elated that it mirrored my own view on creativity. In 2015, Mordvintsev worked as an engineer in Google's labs in Zurich. The problem that really interested him was that one that went right to the core of AI. Namely, we know that artificial neural networks work, but we're not quite sure how. Now, this is a very important problem because artificial neural networks power driverless cars and are at the center of the Internet of Things as well as other devices in the 21st century. Google gives their employees 1 day a week to work on a Google-related problem other than the one they're tasked with, and Mordvintsev chose this one, and he was a quite brave young man to do so. Inspired by the challenge, he got down to conscious work, and he persevered along the path of looking for how researching in computer vision could shed light on the problem of how neural networks function. So I asked him at this point, well, what did you do for the rest of the week? Did you just forget about this problem? And he said, no, it was always on my mind. Indeed, the intense, passionate desire to solve a problem keeps it alive in the unconscious. So it was just after midnight on 18 May 2015 that Mordvintsev awoke with a start. He thought he heard a sound in the living room. Was there an intruder in the house? He leapt out of bed, ran inside. There was no one there. And then he said to me, he suddenly found himself surrounded by beautiful ideas. And one of them crystallized to a point where he could begin programming. This was the solution or illumination of the problem of how do artificial neural networks function? And it's more or less along these lines. He realized that what one should do is to present the target image to the machine, stop analysis partway through at a certain layer of neurons, and then ask the machine, what do you see at this point? And it was for this purpose that he created Deep Dream. Then he went into the verification phase, in which he cleaned up the solution and worked at white heat till 2 a.m. in the morning, writing code and writing a detailed technical report. Then he used the code on this JPEG. He used only the cat part, the part with the adorable cat against the verdant background, fed it to the machine, stopped analysis partway through, asked the machine, as he put it, what do you see right now? And whatever you see, I want more of it. Remember, the machine is running Deep Dream. And this is what the machine saw. After several iterations, inserting and reinserting the image, it saw this, surreal, amazing, sometimes known as the monster beast. It's a cat-like thing with 2 additional eyes on its forehead 2 eyes on its haunches, and canine attributes distributed over its body. The verdant background is now a mosaic with spiders crawling on it. What's going on here is that deep dream overinterprets an image. And this is useful because it allows us to focus on a particular neuron or collection of neurons in a layer of neurons and see how they contribute to an emergent image. In other words, deep dream gives us a sense of the level of abstraction that a particular layer of neuron has achieved based on what's in its memory. Okay, so we've looked at human creativity. Let's now look at machine creativity. Now, like us, computers are problem-oriented and work with the data in their memory. There is no conscious thought level because presently computers have no consciousness. Instead, we give them a problem to work on, they mull over it in an unconscious state, taking into account all the data in their memory, and hopefully they will come up with a solution. Let's take a look at some creative machines I mentioned earlier. This is AlphaGo. It runs on an artificial neural network. It's an algorithm that was created at DeepMind in London. In 2016, it defeated the highly regarded Go master Lee Sedol. In fact, it trounced him. And at that point, everyone agreed that the game of Go had been cracked by a machine, the venerable game of Go. AlphaGo learned how to play Go. That is to say, taught itself by studying over 30 million board positions taken from games played by Go masters. And then it reinforced that knowledge by playing against itself millions of times. Now, AlphaGo made many extraordinary moves, but the move that everyone remembers is move number 37 in the second of the 5 games match. It was a move that you were not supposed to make at that point in a game of Go. And in fact, Lee and the AlphaGo team thought that the machine had hit a glitch, but very quickly realized it was a killer move. In fact, it turns out that the machine had calculated that the probability of a human being to make that move was 1 in 10,000. This was more than a glimmer of creativity. Now, let's feed to a machine equipped with Deep Dream, Vincent van Gogh's painting, Starry Night. Stop analysis partway through, ask the machine, what do you see? Well, the machine sees this. We don't see that. So while AlphaGo can imagine things we cannot, Deep Dream sees things we cannot. Now, until 2014, artificial neural networks were very good at identifying faces and animals, but not so good at generating images. Then generative adversarial networks came on the scene. A generative adversarial network is made up of 2 networks. One is a generator network that generates images from nothing, that is noise, and a discriminator network. Then there is a discriminator network, which assesses these images as to whether they're real or not relative to what's in its database. So with GAN allowed artificial neural networks to imagine, to dream. GANs took the AI world by storm. Let's see what they can do in art. Mario Klingemann is a pioneering AI artist. An AI artist is a new breed of artist. An AI artist is artist and technologist rolled into one. The AI artist creates with code. Now, as Klingemann said to me, human creativity is limited. And I wholeheartedly agreed, because the implication is that machine creativity is unlimited. Here are 2 images that Klingemann created with GAN from his vast repertoire of images. They are surprising. In fact, they're unsettling. They're novel, complex, and ambiguous. They check all the boxes for creativity. In fact, Klingemann considers them to be partway between the painterly and the digital. Ahmed El Gamal is a computer scientist / art aficionado for whom art style is everything. He created an algorithm he calls Creative Adversarial Network, which is a spin-off of GAN. He trained his artificial neural network on over 80,000 images from Western art, spanning the years 1400 to 2000, essentially most of the canon of Western art, and then said to the machine, create me a new art style. And it did. These are images created in a new art style, never before seen. They're surprising, novel, complex, ambiguous. In fact, humans sometimes think that these images were made by a human artist, but surprise, surprise, they were made by a machine. And the kicker is that human judges assess the quality of many of these images to be better than the quality of a lot of work on exhibit at the 2016 Art Basel Fair. Now that must have ruffled a lot of feathers in the art community. I want to turn next to an example of AI-created music in which an AI device and a musician each bootstrap the other's creativity. I have in mind Francois Pachet's Continuator. Francois Pachet is a computer scientist / musician who presently directs the Spotify Creative Technical Research Lab in Paris. Pachet said to me, how do you compose a compelling song? A song that remains in your head and the heads of millions of people. And by song, he included melodies from improvisation. Pachet is keen on jazz. A few years ago, he came up with the problem of how can I increase a musician's creativity in improvisation? And the solution was the continuator. Let's look at how the continuator works. The musician begins improvising. This train of notes are fed to continuator, which parses them into phrases, and then the phrases are fed to a phrase analyzer, which looks for patterns. And it is along these lines that continuator improvises, creates an improvisation based on a musician's improvisation. Musician took his hands off the keys, continuator cut in seamlessly. Now, improvisation is usually defined as a discussion between a musician and a musical instrument. Here is a discussion between a musician and an AI. Now let's pause before taking a plunge into discussing whether machines can have human characteristics of creativity and so be creative like us. We have seen that even in their current somewhat narrow state, machines have shown glimmers of creativity. And that's a substantial step forward. Now, when humans make a great leap forward and produce something that goes way beyond the material they have to work with, we call that creativity. So why not recognize a machine's creativity in the same way? Why the pushback? I think that many people balk at the very thought of machines being creative out of fear that this will actually come to pass. But why should creativity be an attribute reserved only for machines? I mean, I should say, why should creativity be an attribute reserved only for us, word only? I think that many people balk at the very thought of machines being creative out of fear that such a thing will actually come to pass. So why should creativity be an attribute reserved only for us? For example, what all definitions of art have in common that I've seen is that they all assert that that the final product must have been instigated by a human being. But why must there always be a human in the loop? Holding this view means that while machines can create art, they can never be artists in their own right. Game over, read no further. But in the age of AI, this argument is totally wrong-headed, ignoring as it does dazzling advances in AI that point to the coming of machines possessing creativity and equipped with emotions, volition, and consciousness. And indeed, today, effective computing is a burgeoning field of computer science. So let's now turn to how machines can have human characteristics of creativity and so be creative like us. And I'll begin with competitiveness. Now, highly creative work often operates in a distinctly Darwinian environment. One must fight for recognition of one's ideas. Great thinkers have been known to steal ideas from competitors. Can machines have this characteristic? A robotics group at the EPFL, as a matter of fact, write of some recent work that sophisticated forms of communication and deceptive signaling can evolve in groups of robots with simple neural networks. In other words, we can evolve robots that can be deceptive, can even lie, forms of emotion. And even among robots, there is survival of the fittest. Now, a key element of creativity is unpredictability, going beyond logic, often the result of unconscious thought. Might it be possible for machines too to be unpredictable? Well, as it happens, machines have unpredictability built in. We recall the move number 37 from AlphaGo. Another example is that a machine is a complex combination of parts, each of which is designed according to the laws of Newtonian science, with determinism and causality. But when you put all these parts together, there's a possibility for chaotic behavior to emerge, that is unpredictability. This can happen, for example, because numbers are exchanged between various parts of the machine, and these numbers must be rounded off. Rounding off incurs a tiny bit of imprecision, which can snowball into a chaotic event or unpredictability. This is like the butterfly effect, where a tiny butterfly in Brazil can flutter its wings and cause a massive storm in the Northern Hemisphere. Now, in humans, emotions plus unpredictability can trigger creativity. So can machines have emotions? Actually, competition and unpredictability are already emotions. People might argue that machines cannot be truly creative because they are not out there in the world, having emotional experiences like communing with nature and falling in love, but they can acquire such knowledge vicariously. In the not too distant future, machines will be able to read a language fluently and so be able to truly read the web and acquire more knowledge that we can in a lifetime, and so convince themselves and us that they have such experiences that seem to be essential to creativity, like inspiration, love, hate, and anger. And we will wire up machines with complex systems of sensors, regulatory mechanisms, and communication pathways by means of which they will evolve a set of emotions that are duplicates of ours. Now, this is a gorgeous lady I met 3 years ago. Turns out she's a sex bot. Presently, they have clumsy responses and comic book-like features, but that will be all fixed up in the future. And one can imagine sex bots undoubtedly transforming human relations. But by then, the notion of what it is to be a human being will have been dramatically transformed. Indeed, perhaps in the future, artificial intimacy will be the real intimacy. Now, a stumbling block in creative machines is that machines don't have the awareness, don't have the clue that they've made a beautiful move in chess or Go, that they painted a beautiful image, and certainly robot comedians are not at all aware that they have just cracked a hilarious joke. Now, machines cannot be considered to be truly creative until they have emotions, awareness, volition, and consciousness that will also give them the urge to create. Now, what is consciousness, and will machines ever have it? Two key elements essential to consciousness are awareness and self-awareness. Machines have a low-level sense of self-awareness in that they're aware of their circuits and of the problem they're working on. Now, consciousness is our essence. It's our inner life. It's crucial for our creativity. Many philosophers argue that consciousness is such a private realm of being that it cannot be investigated with science. But in the age of AI, the problem of consciousness has moved from the philosophical to the scientific. After struggling with the problem of consciousness for some years, I have concluded that it results from the data processing of information by the 100 billion neurons in our brain. And so consciousness is computable, it's reducible to numbers, and so there's no reason why computers cannot have consciousness. For details, I refer you to my book, The Artist in the Machine. I want to say a few words now about problem discovery, that is to say, discovering the proper research problem and finding connections between disciplines that seem to have nothing to do with one another. This is the realm of research of people of the ilk of Einstein, but I'm not restricting considerations only to scientists. I'm including also artists, musicians, and writers, because all these people can make breakthroughs which can alter the course of their disciplines. Do machines can machines make such breakthroughs? Astonishingly, they have the potential to do so, because text and equations can be encoded in numbers, and numbers are the grist for the mill of artificial neural networks, shown here in all their glory next to Einstein. Now let's look into the future in an artificial network in the future. jam-packed with every bit of knowledge that had ever accrued on the planet. And we set it loose on the field of physics. And it sees a part of that field that's beset with redundancies and inconsistencies, which is sometimes a sign that the wrong problem is being considered, or perhaps the research is going along the wrong path. The machine will look at concepts indigenous to that beset field, and then look at parts, and then look at concepts from other fields of physics that touch on that field, and then look at other concepts that just barely touch on it, tangentially touch on it, concepts in fields such as art, history, music, philosophy, and bang, lo and behold, one of them makes a big difference and gives the machine the clue to look for a new problem or a new path of research. Now, to come back to today, there are large-scale collaborations between scientists and machines, in particular artificial neural networks. I have in mind medical scientists and the artificial neural network called semantics, the algorithm called Semantic Scholar, created at the Allen Institute, which has the capability of looking for relationships among 200 million scientific papers. And I mean here medical scientific papers and the scientists, medical scientists. And the problem that many of these collaborations are working on is how to better understand COVID-19. And the hypotheses that will emerge from such collaborations will be wider and deeper than the hypotheses that can emerge from a scientist working alone. So as with Deep Dream, AlphaGo, GAN, and CAN, machines can imagine and see what we cannot. Today, I've begun with human creativity and then moved to machine creativity and then to collaborations between humans and machines. All this points to a future in which creative machines will work by themselves. This means that in the perhaps not too distant future, machines will have evolved that have a consciousness, a set of emotions, and a creativity that are duplicates of ours. These machines will be as smart as us. This will be the age of artificial general intelligence, in which the line between artificial intelligence, which I always consider to be a terrible oxymoron, and human intelligence will be erased, and there will be only intelligence. Then, not too many years beyond that, machines will have evolved that are much, much, much smarter than us. This is the age of artificial superintelligence. These machines may well have emotions and a consciousness which differ from ours in some way we cannot even imagine. And that's reasonable because machine physiology differs from ours. Right now, it's a silicon physiology. Who knows what it will be then? But one thing is for certain, that the creativity of these machines will far, far, far surpass our creativity, because machines have the potential for unlimited creativity. Well, we may ask at this point, and what's our role going to be in all this? Are we going to be relegated to be household pets, as many silly dystopian scenarios envision? But it's a very, very complex question, what our role will be in the age of artificial superintelligence. Because by that time, the notion of what it will be to be a human being will have been dramatically transformed, because we are merging with machines. And that might not be such a bad idea, because that might be a road to the survival of the human race. Again, whatever human by that time will mean, because machines have the potential to see into the future, see problems, and begin to work on them. Something that we don't seem to be very good at. Thank you.
Thank you very much, author, for your presentation. It's really interesting to see the way how currently the field is evolving and also your takes on it. So we have quite some time for questions from audience, and I would like to invite everyone to use the chat option either in the swap card or on YouTube on the right side and pose your question there. And while everyone probably jumped at doing that, we have the first question about what do you think, what would be your guess about the next domain of arts that would be impacted by AI?
Well, all of art will be impacted by AI, but what we want to do is see machines produce art that we cannot even imagine. You know, and we should not try to discuss this art or discuss this art on the basis of whether it can be distinguished from art produced by us. So machines right now are changing all of art. There's some very interesting collaborations between human artists and machines. And in fact, machine art has hit the high end of the art market. You all probably saw that a piece of AI created art went for $432,000, sold at Christie's.
Thank you. Do you think that we will need to design some kind of a test to know if an AI is actually creative, you know, like something like a Turing test?
Well, we will know that we don't have to design a Turing test. Turing test can be easily fooled. What we really want to see is, again, art that we have never seen before, that we cannot imagine. I mean, not only art, I mean music as well, and literature too. When I first started to write my book, I thought that I knew something about AI created art, AI created music, but not very much about AI created literature. And I thought to myself, is there enough to write a chapter on it? And there was more than enough. AI created literature is extremely exciting because machines are changing transforming language and changing the course of literature. And GPT-3 and et cetera will be extremely important along their own lines, but also for priming us to a certain degree of how we will receive AI created literature. How we will be able to interpret it, I should say. Because it may be that some hundreds, maybe thousands of years in the future, machines will be producing literature, and they will of such a sort that we cannot understand, and they will have to explain it to us.
Thank you, sir.
Well, let me also say that we should all keep in mind big questions like, can machines be creative, and can machines produce art? But we should also keep in mind the question of, can we learn to appreciate art that we know has been created by a machine? Go on.
Thank you. I will pose one more question from the audience. Do you think that students today at any level, including primary school, are aware enough about AI as a concept and artistic side of it?
Whether they're aware of it?
So the question...
They should certainly be aware of it, yes. I mean, these works of art, these phenomena are exhibited in museums. There's a lot of literature about them. The artists themselves go around and give lectures on what they do and where this will go in the future. So it's machines deciding that they want to create a piece of art. I mean, there's a low-level sense of that now. We can take a painting bot out into the countryside, put a webcam camera on it, and let it look around, and it will be attracted to a particular form based on what's in its memory. And there will be a rising in it. There will be a reaction in its neurons, much like we have a reaction in our neurons when we see something and we say to ourselves, I would like to paint that.
While working on the book, did you have a chance maybe to also try some to create some of the AI aided medium? I even don't specify, would it be music or some kind of painting? Have you done some experimenting in this field?
No, not myself, but I certainly intend doing it. Oh, well, actually, that's not true. It takes very little technical ability to produce AI art now. You don't even have to download an app. You can go to, I think it's called a link called deepart.com. And it works on, and it will ask you for a JPEG. And then you put in that JPEG, and then you can put in a JPEG of an artist that you would like to have imagined could have painted your picture. So I'm very keen on Picasso. So I put in one of Picasso's very early cubist, very cubist images. And it what the algorithm did was to put the two of them together, meld the two of them together, so that I had a portrait of myself, in quotes, done by Picasso. So you can actually do that. My background is in theoretical physics, and I've done a lot of research in cognitive science, history and philosophy of science, and so on. I've read a lot about AI, written a lot about AI, but have not done any experiments myself.
Thank you. We have a very unusual question, which states as following: could AI have emerged elsewhere in outer space?
Oh yes, by all means. There's no reason why there shouldn't be intelligences out there, and who can visit us also. But it will probably be the case that, in fact, the ETs that exist out there, and will probably come to visit us, will be bots. They will be artificial life forms, or these civilizations may have figured out a way to have their humans, quote humans, merge with machines, and in that way stay alive. But in our form, we simply won't make it. So yes, there's no reason why there cannot be life out there, and there's no reason why AIs cannot have evolved out there as well.
So another question that I would like to ask is called, how can we ensure that not only large companies like Google, but also smaller entities can tap into the creative potential of AI?
Well, I guess that might be tough, because there's a lot of money involved in this research. And if you're doing something good, Google will buy you out, and you will of course sell out. So I mean, there's no reason why smaller companies cannot have a big idea, but perhaps to put that big idea into motion will require more than they have on hand.
And one more interesting question: do you think if machines can be happy or feel happy?
Oh yes, machines will have emotions, as I mentioned in the course of my lecture. I don't like the idea of artificial emotions. It's sort of or artificial consciousness. It's sort of an oxymoron in the same way as artificial intelligence is. But yes, they will be able to convince themselves and us that they have those emotions, and then some many years in the future, they will possess a physiology that will allow them to be more expressive, just as we are. I mean, we are basically machines. We are at one level biological machines, muscles and bones and so on. And then at a slightly lower level, chemical machines primed by chemicals and a little bit of electricity. And then at the deepest level, where electrons, protons, neutrons, gluons, the whole zoo of elementary particles, all of which their properties can be understood using the equations of quantum physics, which when put on a computer become numbers. So it's essentially, it's numbers all the way down.
And follow-up question, what will humans' reaction will be then?
Pardon me?
What will be humans' reaction to that, to if this will be happening? What do you think we would, how would we adapt this type of interaction?
Well, by that time, we will have been merging with machines. So it won't be very surprising. I mean, a lot of problems with dystopian scenarios, these silly things you read in newspapers and et cetera, is that it's very dangerous to predict even more than 5 years into the future. I mean, who would have known 20 years ago that we would have a world like we have now? So we have to keep in mind that humans will be dramatically transformed.
Thank you for reiterating on. Maybe some of the questions have been answered during the talk, but I'm very happy that you are sharing. Yes, I think it's really good to reiterate on these topics. And one more question there is, but do you really rule out that consciousness is not computable at all, correct?
Yeah, that's it. Yeah, no, it is computable. because we are computable. There's no reason why consciousness cannot be computable, and so there is no reason why machines cannot have consciousness. I mean, the computability of consciousness is an extremely interesting concept, because it essentially, and I will drop this as a bomb, it does away with the mind. There is no mind. There's a brain on which is representable all of our interactions with the physical world, with our world and the world of our imagination. And so these are all reportable too.
No. And I would like maybe the last question to ask, just to conclude also. So it feels like you are fascinated about the fact that machines can be creative, but is there also a part that you are terrified of?
No, absolutely not. The future with creative machines will be a very good future. Machines will help us in solving problems like COVID-19 and so on. No, it will be a world, in fact, it's lack of AI, which is dangerous. Lack of AI in hospitals can cause deaths, for example. Good AIs in powering cars will save tens of thousands of lives every year when we have driverless cars. So it's not AIs, it's lack of AIs, essentially, that one also must look at as being a dangerous situation.
Thank you very much. So I think that one of the even more deeper topic exploration can be done by reading your book, that we should reading the book that is named The Artist in the Machine, The World of AI-Powered Creativity, that will be published on November 10th in the paperback edition. And for today, we're really glad that there were so many questions and discussion, and we thank you so much for your time that you could have devoted us today, and I wish you a pleasant afternoon and enjoy the rest of the evening.
Well, thank you very much for inviting me on, and I will certainly answer any questions that are written out. Okay, thank you very much. From London.
Hello, everyone. Thank you, Arthur, for the presentation. Thank you, Anna, also for moderating the event. I hope you really like the event. I'm going to close it now. I will be very fast. I won't take too much of your time. On our side, we really had a lot of fun preparing the event for you. So we really hope that you appreciated the event. I would like to thank all the speakers for the talks, and also a big thank you to the organizer on our side, especially Mylène, Hervé, and Anna, and obviously Sylvia, who led the event. I think that was really nice. For you to know, we will also clean the recording of the event, and we will make it available to you. You can also continue using the swap card application. You can also export the contacts that you did in this application. So feel free to leverage that. If you have any questions, you can, of course, contact us on our website, datascience.ch. And otherwise, I wish you a very nice evening and take care.